Can you hear me? Okay. Yes, okay.
Is it okay? Can speak?
Yes, they hear me. Like this is okay. I can start. So, hello, good morning, everybody. Huh? What?
They also say good morning.
Ah, sorry. I was thinking there was a problem. Okay, so it's a long day today. We have two lectures this morning. One is new, this one, where we more highlight on medium and high temperature, because yesterday low temperature has been seen. For electricity generation. Okay, so if it is for electricity generation, we need also to deal with the storage. It's because you can't imagine to produce electricity only during the day and nothing during the night. So storage is a very important point. So I will deal with that this morning, medium and high temperature solar thermal for electricity generation. That will deal with solar collectors and also the association with storage and what is done. Then, in the second part of this morning, we will continue the story about PV design, and we finish the lecture about the PV design. We started yesterday about identification of all the components that are required for PV installation. And that will allow us to deal with some tutorials this afternoon. This afternoon, we will have one tutorial on hybrid photovoltaic thermal collector with phase change materials. So I will just start quickly to have an overview of what is a hybrid PVT, what has been done. And then we will see the evaluation of energy performance and exergy performance of such collector. In the second part, as it is mentioned on the program, it is mentioned to presentation of PolySun. But after thinking about that, it's only 1 hour. So I think there is no interest to show you. I will show you some tools. But there is no interest that me, by myself, I show you the tools in 1 hour. You will see nothing special. I prefer to make a tutorial on what is in the backside of these tools. So how they manage to exactly compute the position of the sun in the sky, how they manage to calculate some mask. I will show you some output of such a tools, and what they are dealing, and we make a small application on PV, autonomous PV design central, okay? I think it will be whole for the day. So I will start now by this. So don't hesitate if you have some question following my speech. We can stop. Okay, so if I have a highlight of the sun, if we compare the amount of energy that is available on Earth due to wind, biomass, hydro, geothermal, and energy coming from the sun, there is no comparison. The energy coming from the sun, it's much higher than all the other. And it could allow to reach 10,000 times world of energy consumption. The spectrum of the radiation is mainly centered in the visible in short wavelengths. It's very energetic on this. And so for PV, as I mentioned yesterday, we are using in the visible range of wavelengths around 1.2 micrometers for classical silicon components. Okay, see if yesterday it has also been dealt with my colleague about the solar constants. So solar constants out of atmosphere, he has demonstrated that it was 1,368 watt per square meters, and we assume that the radiation which is impacting the Earth is around 25% of this, and so around, in the mean, 342 watt per square meter. Okay, it's also consider, of course, the night in one side of the. So it's another way to present this time constant and this solar constant and what is impacting the Earth in mean. Just to remind you also, depending of the position where you are in Earth and of the position of the Sun, the radiation which is coming through the atmosphere, where depending on the inclination of the Sun and where you are on the planet, could cross one atmosphere. We say the air mass is 1.5, 2 atmosphere, if you are depending on the position. So for PV, as I mentioned previously, the tests are made with an equivalent of 1.5 atmosphere mass. That means that there is, of course, the path is very important because all along the atmosphere, it has also been shown by Pankaj yesterday that there is absorption of the radiation by some gases. Okay, so it is important to consider which is crossed. So I will go on this. What is arriving at the on Earth? So as I told, the mean is 342 watts per square meter. There is multi phenomena that are implied. Only, but it's enough to warm up when there is greenhouse effect. 50% of this energy is absorbed by the surface of the Earth. Sorry. 20% is absorbed by the atmosphere, by the clouds. Around 20% is reflected by these clouds. So go back in the space. And 4% by the terrestrial surface. So it's more or less what happens. As it has been mentioned also, there is many different kind of radiation when you are on Earth. Some is coming directly, straight to you. So it's direct radiation. Some is reflected. Some is coming from the diffusion of the atmosphere. So what is the part which is reflected and coming from the diffusion of the atmosphere is said diffuse radiation when we consider the modeling at the scale of a building. It could be very important, this reflection part. It depends on the emissivity, reflectivity of the ground. Okay, so the albedo in some country where you have some snow, the part which is reflected could be very important. So now regarding the generation of electricity, there is 3 main sectors. So 2 main sectors for electricity: photovoltaic at the top, as we have seen yesterday, and thermal at high temperature. High temperature is considered to be over 300 degrees to 1000 degree. When it is down, when it is lower, it's hard to use it as energy vector for generation of electricity, so we use it as domestic hot water or direct solar floor heating, thing like this. So regarding the flat plate collector, the most simple, so at low temperature, very low temperature, is uncovered, so there is no glass, there is only an absorber, and there is that means that there is no greenhouse effect. Okay, the radiation is collected by the absorber, but it's also a part is also emitted in infrared, not stopped by a glass. Okay, so this could be used for drying some fruits, heating some swimming pool, heating some big industrial container because the temperature is not so high. Could be useful. Then you have the covered flat plate collector. So it has been widely studied yesterday, but we had a glass, okay, between the absorber and the outside part that allow to keep, in terms of emission, the infrared emitted by the absorber of the solar collector. Vacuum tube. So when you are in a flat plate collector, you have a glass, you have air, you have absorber. So you can have some loss by convection between the absorber and the glass. Okay, the hot air coming from the absorber is going to the glass, and the glass exchange with external part. So you are losing a part of heat due to convection of the air between the glass and the absorber. When you evacuate this air, so there is no air, no gas, you erase this loss due to convection between air and absorber. Of course, it couldn't have a flat shape, because if you lay it like a flat shape, there will be an implosion of your glass. Okay, so it is in this way that there is a cylinder. Okay. So for low and medium temperature, the main application is for residential heating and domestic hot water. You can use it for industrial process that could require hot water. Typically for cleaning, there is a lot of industrial process like yogurt manufacture or milk. They need hot water to clean the big tank of food, and so it could be useful. It could also for drying, solar cooling. We will see some application of solar cooling with thermal energy. And so yes, the cost of course of evacuate tubes that allow to reach the higher level of temperature is higher. It's 1.5 or 2 times higher than the flat plate collector, which is quite common and standard. The performance of vacuum collector does not depend on wind or outside temperature due to the fact that there is no convection inside the collector to bring heat to the glass. Okay. It could be useful also for when you have a lot of energy need in terms of temperature. So typically it's hotel or hospital that need a lot of hot water and also to cool. So for the main problem of solar energy is it is a low density energy compared to the other. Of course, there is abundance of solar energy on Earth, but you can see the mean it is only 342 watt per square meter, the mean surface of the Earth. Whereas, so you need big surface, but even with big surface, you don't reach very high temperature. So if you want to reach high temperature, you are obliged to concentrate, okay? And so that's why if you want to have high temperature, you go on the concentration. You have to multiply on the same surface the equivalent of sun, okay? It is this. So the geometric concentration factor is the ratio between reflector area. So you are, to concentrate, you are using mirror to focus on the same surface. Reflector area divided by the receiver area. Okay? So the higher the concentration factor, the higher the temperature is reached. Okay? Usually you have a huge reflector area and a small receiver area. Okay, if you have a lot of mirror focusing on this receiver, each mirror is the equivalent, if it is very clean, of one sun. Okay, so you multiply the sun on the same area. So there is multiple application, cooking, seawater desalination, more and more, because there is in some part crisis of fresh water. Pollutant treatment also, and especially microplastic in some water. Now there is some attempt to concentrate at very high temperature, or to use also UV treatment with the sun, photoprocess for this. Synthesis of nanomaterials, materials qualification, power generation, even why not cement generation. When we are speaking about concrete, the carbon footprint of concrete is very huge, and the main part of the carbon footprint of concrete is related to the cement, which require to be in furnace at a temperature over 1000 degrees. So you can reach such temperature with solar concentration, and there is some attempt about replacing furnace for the generation of cement by concentration. It has been shown yesterday, so you have what we call the dish, so two axis rotation. At the center part, I can here. So there is a parabol which is focusing on this engine, which is a Stirling engine that allow to generate electricity. So the Stirling engine is a dilatation and compression of air, like a piston, okay, that allow to generate electricity. You have one rotation axis. Concentration factor is lower than 100, but it could be enough for generating electricity. Usually in the focal, so the tube that you see, it's not water, it's oil, to be able to go over 100 degrees. I didn't say that the concentration factor of a dish is around 10,000 vocal, okay? So that means that in principle, on the small surface of the Stirling engine, you have 10,000 times the sun radiation, okay? If the dish is clean. If it's not clean, performance is decreasing very fast. Mirror has to be very clean. Then you have a mobile reflector. We call that heliostat, and with tower. So they reflect all the radiation on tower. So that means that we have to manage perfectly the inclination and the direction of the mirror to focus on this tower. Okay, there is 2 axes of rotation for the heliostat, and the tower is fixed. Okay, with one receiver. Concentration factor is around 3,000. Okay. Here you have the solar furnace. So you have, sorry, it's in French. At the bottom axis is concentration factor. Okay, so you can reach 30,000 times solar energy in the same surface. Okay, so you can reach around 3,000 degrees, 4,000 degrees with such concentration. Okay, so it's hard to reach. I will show you one application. Then between 10,000 to 20,000, you need to be very careful on the management of the concentration. Typically, it could be with heliostat. You have big central with tower and concentration. And then lower, so between 2,000 and 10,000 concentration factor, it's quite easy. Okay. And so you can see the level of temperature that you can reach. You can reach over 4,000 degrees in one surface. So Gilles Flamand, which is the author of this, is very famous in the field of solar concentration because he was the head of, I will show you this nice laboratory in the Pyrenees, so in altitude. Why in altitude? Because the mass of atmosphere is lower. Okay, when you are very high in altitude, the AM is lower. And also you have less pollution, less particles in the atmosphere and so on. So you can reach very pure radiation on the surface. Okay, so it's with such a condition that they were able to reach over 4,000 degrees. On this is a lab in the Pyrenees. So it is the solar furnace of ODEO. You can see the lab is 6th floor, okay, and the parabole is the building, the whole building that will. So all the mirrors are concentrating solar energy here in one surface, which is like this. Okay. So have you seen the number of mirrors? I didn't remember how much, but I think close to 20,000 mirrors. Okay. So here the question is that the south is behind the building. So it's strange. There's something missing. Yes, if you look, the parabole is not in the sun. It is in the north. So what is missing is that facing this, there is a big field of mirror. Okay, so the sun is here. Okay, the mirror are here. So it is related to the fact that it is in the mountain. And the mirror are all concentrating solar energy on this parabole, and this parabole is concentrating all the energy here. Okay? So that allow, because this is fixed, thanks to that, you allow to follow the sun and to reflect on the parabole. Of course, the building couldn't rotate like this so easily, So the principle, yes, it is this mirror follows the sun and injects the solar radiation on the parabol. This has been built, the first construction of this, the starting point of the construction of this was in 1960. So very, very long time ago. It almost disappeared because after, in the 1980s, France has developed nuclear energy a lot and stopped to work on solar energy. It was also almost all the mirrors were broken and things like that. And it is thanks to European project that this device restart in 2000, and the main research that were made with the European project is to work on the space application, aerospace application, and to work on some special materials, you know, for the space aircraft when they are coming in the atmosphere. They need to be very well protected because there is some friction and the temperature of the materials are coming very high. And it is thanks for the research in space that this has been restarted, because they were at the beginning testing such materials for aircraft coming in the atmosphere, because they were able to reach high level of temperature, more than 4,000 degrees, and to test that, okay? And then after, for other applications, they have tested to make some cement, treatment of waste. They are doing a lot of things.
What maximum temperature they have reported?
They could reach around 4,600 degrees. The records, yes. So here you can see the wool. So they are fixing the sun and reflect on the parabol, which reflects here. Okay. Here, if you cross, you disappear. You can throw a wood and disappear. Okay, so it's very dangerous. Of course, you have to manage very well the heliostat and things.
Accident, like some bird is flying and then.
No, never. No. In a tower, in another place, there is a tower. So there is this system where they are also testing the management of the heliostat, and you see on the tower that they made a fault in the focus, and it has attacked the bottom of the tower. So yes, it's really impressive, and you see that it is in the mountain. You can reach 1 megawatt power. It started to be built in 1960 and finished in 1970. And so they study a lot of different materials, behavior, resistance, under high temperature. If you go in this area, it is in southwest of France. It's very impressive to go and see that. It's really very, very nice. So the laboratory is Promes, which is in Perpignan and also in Odeillo. So if you have this summary, so concentrator with a tower, so and then after you have the system. So the system is to generate heat. So for example, now for the tower, the fluid is air. Okay, it's air. They are injecting the radiation in a kind of porous materials. At the backside of these porous materials, there is air, and those they take this air at high temperature, then heat exchanger with water or oil, and then go on storage. We'll see the storage. And generation, the same. After, the principle is the same, as to generate some steam, and then to use turbine and to generate electricity. Okay, so whatever you have a Fresnel. So Fresnel, it's some mirrors that are reflecting in a horizontal focus. Okay. There is also some industrial application of that, and you have cylindro-parabolic vector. Okay, so Fresnel is like this. It is you have one focal, and finally you are building a kind of big parabol. Okay, the level of ground to concentrate. So it's a lot of different mirrors that also manage to concentrate. So it's very interesting to work on the management of heliostat and of mirror. There is a very interesting mathematical computation to deal with that. And of course, the complexity is depending on the number of heliostat, especially also with the tower. It's very difficult to very well adjust each heliostat rays to focus on the tower. So advantage, it's cheaper than the flat mirror because it's flat mirror. It is flat mirror, so it's cheaper than parabol. Okay, because you are mimicking a kind of parabol with flat mirror. Okay. It's lighter infrastructure. Disadvantage is optical performance is not so good as a parabol, around 30% less. But the main objective is to reach the sufficient high level of temperature, around at least 250 degrees, to generate steam and then electricity. Okay, when you have a summary of, you have to manage the heliostat, so the movement of the mirror. So you have also the receiver, that could be the tower, that could be another parabol as you see for the furnace. Then you are taking the hot fluid that could be oil or air, depending on the level of temperature. For such tower, it's generally not directly now steam, it's more air with high pressure, high temperature. Then there is heat exchanger with allow to generate steam, water steam. You have a turbine, okay, so steam tower, turbine, and injection on the grid. As I mentioned, for such a device, you are obliged to have thermal storage. Even if you are in a desert, where every day it's sunny, during the night you have no sun. So it's rare that a country don't need electricity also during the night. Okay, so most of the time you have solar, you have thermal storage. Okay. So here it's also another way to show you operating principle. And so you have different also thermodynamic cycle that allow to recover after the steam, to recover part of heat when the steam is condensate, okay, and so on and so on. Of course, when the steam is in a closed loop, so you can recover a part of heat when the steam will be condensate as liquid water. Okay, some example in Spain here, Solar Central. There is 1,255 heliostat around the tower. Okay, the surface of heliostat, so the concentration factor is surface is 120 divided by the reservoir. The reservoir is around 1 square meter, not so much. Okay, so the power that is produced is 20 megawatt. And such a central allow to produce energy for 10,000 dwelling houses. It's okay? Okay. Okay, so avoid emission of CO2 and so on and so on. Here you have biggest also central, you can see you have you have 2 towers and 2 fields of heliostat. Okay. You have also a cylindro-parabolic collector, so it's a big solar high level of temperature, solar concentration. I think the biggest one at that time is in Israel, if I didn't remember. So some example of different units. United Arab Emirates, a capacity of 700 megawatt. You have Morocco, United States, several ones. One of the most recent is in United Arab Emirates with parabolic and solar power tower. Okay, so it's a mix between linear parabolic and tower. But I think the last two, yes, one of the last one is in Israel. Temperature range. So for parabolic, you can reach between 300 degree to 400 degree. With tower, you can reach 1,000 degree. Depend of the number of heliostat. Okay. Most you have the field of heliostat is bigger, the more the concentration is, and the level of temperature. So you can reach what are the strengths and challenge for such things. I don't know if you have some question on concentration. I just want to show you low temperature, solar low temperature generation of electricity. It's quite, I like this principle. It's not really developed, but I like this principle. But regarding the medium and high temperature, do you have some question about this concentration? It's okay. It's okay.
That plant, what you have shown, which was built in 1960s, now people are doing some research, right?
Yes, it's fully dedicated for research.
Now it is your personal.
Now it's still a research lab from CNRS, and they keep on working on not really on concentration. Now they master the concentration since a long time. The management of heliostat also, they manage that, but they try to find new application for such furnace. What we can do. So they have developed some process to separate rare earths, for example, to lithium, to separate that, to treat some waste, to generate cement without consuming petrol and gas, so try to find new application. One of the applications that has been started to be studied, but is not really very efficient, is instead of the mirror, instead of the heliostat, why not putting some PV panels? Because it's glass, so in principle glass is also reflecting a part, but it's not really concluding. Okay, so there was a attempt to make hybrid PV concentrate solar using PV panels on the heliostat, because heliostat in principle is very well oriented. It's a kind of sun tracker finally. So if you put PV on the heliostat, it's good for the PV production. And so they were expecting to recover a part of the concentration, but of course you are losing a lot compared to a mirror. Okay.
You need more cooling.
Yes. Yes.
In the dish collector system, the temperature is very high, so for water.
Yes.
How the phase change, huge pressure, that will be managed?
For the steam generation, it's well managed, because yes, high pressure vapor is well managed since a long time for a classical burner. I didn't investigate on this topic very much, but it's a classical steam turbine that is used also for coal power generation. They burn some coal for generation of steam and then to use a turbine, but I don't really focus on that. Sorry. Other question? So this application finally could be solar, low temperature generation of electricity. It is called solar pond. Okay, you have here a real development. So it's a large-scale energy collectors with water, with salt water. Okay, so you can use also this large surface as thermal storage, and it could generate a part of electricity due to the difference of salinization, difference of temperature. One is already working since 1988 in Bet Arava in Israel. His area, of course, is large. It's large area, 210,000 square meter, and it produces 5 megawatt. Okay, so it's funny because we said that with low temperature we can't produce electricity, and this system can. So it is based on a different zone. So it's a basin which is not deep. Okay, it's a large area of salt water, but not deep. So you have different of salinity profile, okay, and temperature profile, which are following the same in such a kind of components. So you have a upper convection zone, okay, because it's irradiate, okay, a zone which is non-convection zone, and at the bottom a lower convection zone. Okay, so you have convection down and at the top. So it could be considered as divided in 3 zones. So this solar pond is composed of salted water, okay, and the salt concentration is increasing with the depth. Of course, the density of water is higher, and from a very low value at the surface. Okay, because at the surface there is evaporation due to the sun radiation, so the concentration in salt is lower than at the bottom. Okay. So when you look at the physical phenomena, you have this, you have convection zone at the top, convection zone at the bottom, nothing in between. And so much of the sunlight reaches the bottom, okay. The bottom is heated, okay. It's reached the bottom because the depth is not high, okay, and the bottom is dark, so it will allow to heat the bottom. The salt water cannot rise because it is heavier. The density of salt water is heavier, so it couldn't move at the top, and thus the upper layer prevent convection current from forming. Okay, so there is two different zones. Without loss of heat, the bottom of the pond could reach 90 degrees. Okay. And so the description, I didn't focus too much on it, but the principle is that there is a transfer due to the salinity concentration, there is a transfer of electrons which are collected on this big surface and allow to generate a small amount of electricity. Compared to the surface, it is small amount of electricity, but if you are in the desert, for example, in Salt Lake, you can expect to have interesting production, even if the surface is large. It is the same for the tower of concentration with a large field of heliostat. Okay. So the temperature is nearly close to the ambient temperature at the top. The salt concentration is also near the clean water, okay? So like fresh water. Due to the contact between the top layer of this zone and the ambient, there is energy loss from convection and evaporation. So it seems to be obvious. The next zone, so in the middle, is non-convection zone. The salt concentration inside this zone is changed with the depth, so you can see it's not constant compared to the upper layer and the bottom layer. And the increasing of the depth from this interface results in the increasing of salt concentration. Okay, the last zone, so the lower concentration is the most salt concentrate zone, and also the higher level of temperature, as I mentioned, because as it is not so, the depth is not so high, the radiation is going till the bottom. Okay, so it's a mix between thermosiphon and then there is yes, a recover part of electron due to the difference of salinity. So this kind of component have been started to be studied in 1948, and there is now some kind of application. We don't find too much information about that. We know that there is real application, so it could be interesting also to study that. I just discovered this kind with my students this year because I give them some bibliography about solar application, and some have identified that. I never saw that before. And I found it was interesting to share it with you because finally it's a kind of solar low temperature generation of electricity. Okay. The efficiency is around 15 to 20%. So the pond efficiency is defined as the ratio between the quantity of heat extracted from the pond divided by the solar insolation of the pond area. The efficiency for electric energy is not very high. As I told you, you need very big surface, but for real application, it has been proved that you can reach some power. So it's 0.8 to 2%. And for a typical area in the Middle East, where the global radiation could be estimated at 2,200 kilowatt-hour per square meter per year, you can expect to generate electricity between 20 to 45 kilowatt-hour per square meter per year. And heat energy, it's a hybrid system that you also generate heat. Okay, so it could be interesting to focus. Disadvantage is that it's not working well at high latitude, and due to evaporation, of course, you need some water at a certain point. Okay, if you are in a desert, if you want this system to continue to operate, you have to inject some water. Otherwise, you will have a dry salt lake without water at the end. Okay, so did you know this kind of collector? No. I don't know if you have some question. I was thinking to add this.
Maintaining the salinity,
Yes.
ingredient.
Yes, you.
Otherwise, no, it will be same concentration.
It's automatic due to the fact that at the upper level there is evaporation and low temperature, and due to the volumic mass, the more high level of concentration is at the bottom, which is also at the higher level of temperature. And so this the process is then operating like this if the depth is not so high.
With time, diffusion will take place.
Hmm?
With time, diffusion will take place. And then you need to maintain some salinity maybe by
Yes, you need, yes.
Is there any ionization?
Yes?
Is there any ionization, because to produce electricity we have some positive and negative charges?
Yes, there is a real...
Here actually no, we use organic Rankine cycle. So here actually heat only we are using, and then at the lateral stage we are using organic Rankine cycle.
Yes.
Low temperature
Yes,
power
yes,
supply.
yes, what is
Mm. So this is a real application that I have identified.
In India also we have.
Ah, you have?
Infuse.
Okay.
Infuse. They have in there. That they use for dairy application.
Okay, okay.
Gujarat.
I find that interesting, yes. Mm.
Gujarat.
Do you have question? I was thinking to have put the solar the storage also, but it will be in my lecture of tomorrow, I think. Sorry. We will see the thermal storage for sure. Do you have question, or maybe we can do a break now? It's okay, or it's too early? Ah, half an hour. I can maybe speak about the thermal storage, so if you want. Okay, I got to find it there. Storage. Ah, sorry. Sorry. Maybe what I suggest is to restart on PV design until the break and then continue on PV design. Okay? Because I didn't remember if it is tomorrow or after tomorrow that I will speak about thermal storage. Okay? Can we put the presentation of yesterday? It was day 1 and 2. Yes. Okay. Like this, we continue a bit on this and. So we are on this, and so we were on the connection of all the components. Okay. So to remind you, for a grid connected, you have the PV central, switch off of this PV central that allow to fireman to disconnect the PV central if there's a problem of fire. You have the inverter, and you have electrical meters. The more complicated is finally for autonomous design, where you had the battery, and we have seen that we have many ways to couple all the components depending of the needs, and so for the management of the charge and discharge and the connection to the battery. Okay. When you are connecting the modules, we have seen that we need to have the same modules per string, the same modules for the whole PV central also. It's dangerous if you combine some different branch of PV modules, because if you have any difference between operating conditions, we call that mismatch effect. You will induce not a very optimal production of the PV central. We have finished on the way to connect the inverter to your PV central. We have seen that the main advantage to have one inverter for the whole central is the price. But the other advantage are in favor of multiplying the inverter in order to avoid, if there's a problem on the PV central, to avoid to generate a mismatch effect and then a bad or a breakdown of the whole PV central. The inverter is very important, so it's an electronic device, okay, and is allowed to maintain a quite stable operating condition. So to maintain a quite stable operating condition is integrate in itself some capacity, okay, so to avoid all the fluctuation. That's why when I was speaking about yesterday's PV coupled to the battery, the main an important device is to add some charge-discharge controller, but if you can also to integrate an inverter, MPP tracker that allow to have a stabilization of the production in both directions, but so it's inducing the integration of battery, of capacity. So if there is capacity, it gives us an idea about the lifetime of such components. Do you have an idea of a lifetime of a capacity? Or and it is the weakest element in a PV central in terms of lifetime. It's like a battery, so finally it's around 8, 9, 10 years. Okay, so lifetime is around about 10 years, 8 years. So when you have a PV central, sometimes there is some economical agreement that, for example, somebody or a PV, energy provider can rent your roof. You say, I want to rent your roof. I will install the PV central. I will sell the electricity. And after 10 years, I will give it back to you. Okay? So you have to be caution if it is just before or just after the inverter collapse. Okay? Because the cost, if you have one PV central with one big inverter, the price could be very expensive. Okay. So it is the weakest, part of PV central. If you are in autonomy also, if you add some batteries, the weakest part will be the battery. The lifetime of the battery is around also the same range, okay, 8 to 10 years. So how the maximum power tracking is operating? It's like by test dichotomy. You are starting, it's an electronic device, okay, it's starting to fix tension, computes the power. Then he had a small discrepancy of tension, of voltage, compute the new power. If the new power is lower, so that means that the maximum, the optimal value of the voltage is lower, so it's going down, so it's decreasing the voltage. See the power generation, if it's bigger, it's going down, okay? It's like this, of course. It is very fast, but also it is using the hill climbing method, okay? So the algorithm is you are changing a bit the voltage, you look at the power, okay? If the power is higher, so it's good, so you are keep on increasing the voltage until the power is not higher, and so you will find finally the maximum power. So it is this way that the maximum power is identified when the PV central is operating. Okay, so of course the quality of the inverter is to be able to compute, to identify this maximum power as soon as possible. So the rapidity to identify this maximum power is very important. Also, the inverter has to be selected in a consistent way compared to the power of the PV central. If the inverter is not well designed, so is over, for example, over estimated, over designed compared to the power, of course, he will all the time find the maximum power, but the accuracy will not be so good if the inverter is too big compared to the power, okay? And if the inverter is lower than the power of the central, when the power will be over the capacity of the inverter will disconnect. It will not be able to find the maximum power because it is under design compared to the global PV power. So it is very important to well design this and to adapt it to the power generated by the central. Here you have an effect of a shading effect. For example, here you have a PV central on the roof, and maybe in the afternoon, after 2 o'clock, the wall which is here is making shadow partially in some modules. Okay, not all the modules, or one module is fully in the shadow, but just a part. You can see here the effect on the intensity, okay, if depending of the number of the cells that are on the shadow. So in yellow, if there is 20% of the cells of the module that are in the shadow, in blue 35%, and you see the impact on the power is huge. Okay, of course it's huge because it's a project. So it's very important also when you are designing the PV central to be aware and to compute the close mask and the far mask. So the mountain and also the building by itself or the surrounding buildings, because you can really impact. So you can have also the impact of the trees between winter and summer. In winter, if the trees have no leaf, it will have no impact. In summer, it could have big impact. You could have a chimney or ventilation system. So a chimney that could be narrow but high could induce all the day long, finally, shadow on the PV central when the sun is running. Okay. Some example of installation here in Munich. You have 3 inverters for a big central. So you have here the panels here. So of 1 megawatt, you have 3 inverters of 330 kilowatt ampere. So the series, for example, here you can have some unit power from 500 watt to 5 kilowatts. So it's small. As I told, the gain is the flexibility, easy maintenance, and of course you have also some disadvantage that you are losing each time you are converting, so you are losing a bit more also because you are multiplying the inverter. An example here also in Germany, for the same power, so 1 megawatt peak, you have 600 inverter of each 1.5 kilowatt hour. And so, as mentioned, if you have 1 inverter per module, the efficiency is a bit less, but after the feedback we have on this kind of installation, you are producing much more electricity within 1 year, because, as I mentioned, if one of the PV panels has a problem of operating, you will not destroy the wool production. Okay. So you have here an example in Amsterdam, in Holland. So it's a long motorway. It's to protect from the noise. So it's a wall, a PV wall, and a noise wall. So for a power of 216 kilowatt peak, you have 2,000 inverters. Okay, so it's a huge difference. Here, interesting solution is if you have multi-string, so you can have several inverters because you want to optimize the production all along the day. So for example, you have a house with roof with 4 different orientation. You can put at the east to start to produce the morning, at the south and at the west. For dwelling house, it's very expensive, but for some tower, could be interesting to study or industrial application. It could be interesting to have 3 different maximum power tracking and inverter. As soon as you have different orientation, even if it is on the same system, as soon as you have different orientation, different local particularities that could induce a difference of operating, you have to distinguish the inverter. Otherwise, you will impact too much your production, and also is not really good for the global inverter that will be connected to the grid. Okay, so this is, you are starting from the PV, the inverter, and to connect the PV panels and all this stuff, you have to use cables. You are obliged to use standard cable because there is big risk about this cable. The main of the current which is crossing this cable is continuous current, so you can have a high level of intensity, and if the cable are not very well designed, you can have some problem and fire problem on PV installation, for example. So, of course, you have to design the section of the wires that able you to transport this intensity. Okay, and so of course it depends of the Joule effect, so the resistance that will, and the Joule effect that will be induced due to the intensity. So the resistance of the cable is depending on the section, and so you have to design it in relation with the intensity which is going through. So there is some standards, okay. This cable also to have a specific envelope, okay. Specific because usually these installations are outside, or the cable are outside, so they are submitted to UV, okay. And the UV is very strong for attacking the polymer, so this cable has to have UV protection, especially because such PV central could have a lifetime around 20 to 25 years, okay? So 25 years outside submitted to UV could be very damaging. You have also to have secure connectors, okay, like this, in order also to, for the installer to be not confused between the plus and the minus when they connect the PV in between, and so to avoid also, of course, water infiltration or other thing like this, so to be fully protected. And yes, the contact resistance has to be very well studied in order to avoid most of the problem when you have seen maybe some problem of PV central on a roof with fire It is because the cable were not very well designed, or the PV panels not plugged as it should have been. It's not related to the PV panels or other electronic components. It's connection and cables that have not been well designed. Okay. Then we start with the battery, and this afternoon we will need that. So a battery, generally for capacity, the unit is coulomb, but we are using equivalents. It's like joule and kilowatt hour. Coulomb and ampere hour is the same kind of transformation. So for battery, we are using the unit of ampere hour. Okay. So when we said that battery has a capacity of 100 ampere hour, that means that it is able to provide 1 ampere during 100 hour, okay, or to be able to provide 10 ampere during 10 hours, or and so on and so on, okay. So you have some standards that, for example, the capacity 10 corresponds to discharge current of 10 hours, okay. For example, if you have a capacity of 100 ampere hour, that means that it will be 10 hours of discharge, 10 ampere, okay. So it is a convention which is used for the battery. One important thing, and after we can maybe make a break on it, it is the number of cycles, okay, and related to the number of cycles is the depth of discharge, okay. So we never discharge completely a battery, which it will, if we do each time 100% of discharge and recharge, the number of cycles will be limited. Okay, the more you are going in the depth of the battery, the more you are limiting the number of cycles. Okay, it's quite simple, and it's not linear. Okay, so that means here it is extracted capacity, okay, but it is the same. So if you are only using 20% of the battery, okay, in terms of discharge, you can have a large amount of cycle. If you are using 100% of the battery, so the depth of discharge is 100%, you see that you are limiting a lot your number of cycles. So when you will have to design it for the PV central, you have to make the choice. And of course, it has a huge economical impact. If you have a lot of money to invest at the beginning, okay, so you are quite comfortable on the design of the battery, and you can say, I will choose the depth of the discharge of 50%, for example. That means I will use it maximum at 50% of the capacity. That means that regarding the real need you have, you will double the size of the capacity. If you use only 50% of the capacity of the battery, regarding your real need, you will double the capacity. So that the price almost multiply by 2. If you have not too much money at the beginning for the investment, but you say that you know that every 3 or 4 years you have money in order to maintain the PV central, you can choose to go deeper in the use of the battery. That will reduce the investment cost. So you can say, okay, I will use my battery at 80%. Okay, but you know that you will reduce the number of cycles. So the lifetime finally. Okay, so you can say, okay, I have not so much money at the investment level, so I choose 80% of discharge, but I know that the lifetime, instead of being 9 years, will be, for example, 6 years or 5 years. Okay, so that in 5 years, for sure, I will have to change. Maybe not all the battery, it's not, but some of the battery I will be obliged to change it. So it depends at the design step. If you have a lot of money for the investment and not after for the maintenance, or if you have not too much money at the investment, but you know that regularly you can inject money for maintenance. Okay, and the price of battery is a very important topic because when you had battery, the price of a PV central is increasing a lot. Okay, but for sure, never design it for 100% of use. Don't forget that, because otherwise you will more than divide it by 2 the lifetime of your battery. After 2 or 3 years, they will be out. Okay. So we can make a break now and continue after. Thank you.
We'll be joining at around 11:15.
Yes.
So 11:15. So please occupy before 15, maybe 11:10, so that 11:15 you can start. There's a tea break, so you can have a cup of tea. So now tutorial.
Hmm?
Now the tutorials. This is afternoon.
Yes. I'm thinking maybe to, after this, to present, because I didn't remember where I put, maybe I put the solar storage. I didn't remember where I planned to put it. Thermal storage, yes, because I was thinking I prepared thermal storage after the high concentration, but I put somewhere else. I don't remember where.
And if you want something, if you want me to take some
to something. I will see what I will do in the second part. Maybe just we'll start the presentation of one tutorial also, because it's long this afternoon. I've got one long tutorial. Okay, I'm thinking. Okay. Okay, so we have finished regarding the battery. It's a very important point, and a key parameter, economical parameter for autonomous PV central, because it's usually as soon as you had some battery, the investment payback time is very long. Okay, compared to PV central, which is directly connected on the grid. As I told you yesterday, the price of PV has considerably decreased the last 10 years, divided by more than 10 in 10 years. So now a PV panels is very cheap compared to 10 years ago. But the main price of autonomous central now is mainly focusing on battery, because of course the battery price didn't change so much. We need a lot of battery for phone, for car now. So there is high level of demand on the battery. So the number of cycles that will be allowed will depend on the depth of the discharge. And so what is important, so with the battery, you can directly connect PV modules on the battery in artisanal small powered system. It is okay, but I strongly advise to take a charge and discharge controller between the battery and the PV central. That will avoid some problem of fluctuation, avoid also some problem of, for example, if big difference between power production, and so it's very important. Okay, so the efficiency of battery charge is quite good, but there is efficiency, as I told you since the beginning. As soon as you are converting, changing, you are losing. So the efficiency of classical battery charge now is around 80%. Okay. But you are losing a bit when you are charging and discharging. So you can imagine if you had 80% of efficiency regarding the charge and you use only 80% of the capacity, you have to multiply twice by 80%. So to increase the real battery that you will buy. Okay. We will see that on a tutorial. Okay, so if you had also an MPPT regulator, you can win energy. Of course, as I told you, it will focus on the maximum power production of PV. And for this, you will have efficiency battery charge, global efficiency charge of 80%, compared to the fact if you don't had maximum power tracking. But now most of the discharge and charge controller that are designed for battery for solar application are including MPP tracker. It's okay. So what we can is to improve the lifetime of, especially its lead acid battery. There is some lithium batteries that are used in some application, but it's very expensive compared to lead acid battery. So it's still the standard we found for typical autonomous installation. So we have to avoid large discharge current. To avoid large charge current, so intensity is it could be high intensity is a problem. To avoid deep overcharge level. Okay, so when if the battery charge, you have to disconnect. Okay, so it is the role of the discharge and charger controller to disconnect, to avoid to inject, to continue to inject some current in the battery when it's full. That is the reason why when you don't put a discharge and charger between PV and battery, it could be a problem to damage the battery when you directly plug some PV panels on the battery. Of course, you have to avoid deep under discharge level. Okay, so the depth of discharge over 80% is dangerous in terms of number of cycles. You have seen it's not linear, so when you are going deeper than 80%, the lifetime is considerably reduced. To store, if possible, when it's fully charged, okay, and operating temperature between 10 and 20 degrees is good for the battery. So finally, you see, the battery and the PV modules have the same challenge in terms of temperature. So PV don't like too much high level of temperature because the efficiency and the aging is increasing, the efficiency is decreasing. It's the same for the battery. So could be a problem for battery for autonomous installation in Africa, for example, where the level of temperature could be high. For the battery, the lifetime of the battery is decreasing also with the temperature. Okay, so you can have a design of a battery rack for, and you estimate that the lifetime will be 9 years old, and for sure if they operate every day around 40-30 degrees, you will have to change some battery before the 9 years. Not all maybe, but some will aging and will be destroyed. So it's very important. So in very, very hot country, the battery rack are stored in a cooling chamber. So it's a paradox because you are generating electricity and a part is used to cool down your system. But it's the same for the inverter. When the inverter has submitted to it's electronic, so they don't like to operate at high temperature like your computer. So if it is too hot, extreme condition, usually battery and inverter are in cooled chamber. Okay, so part of electricity which is generated is injected to cool down some critical elements and especially electronics components. So during use, it's generally good if you don't discharge more than 20% per day. But of course, you can't take this assumption for designing your system, because that means if you just take this assumption that you will only use 20% of the battery capacity, the price will completely explode. So usually you said that you will not use more than 80 or 50% of the capacity to design. But it's better if during the classical day it's around 20% a day. So you see, it's very also delicate component, the battery. It's expensive. the lifetime is not so high compared to lifetime of PV modules, and you don't like extreme operating condition, extreme taking a lot of electricity inside, and also temperature. Okay, you can have also problem of fire. You have seen, I think, a lot of things regarding electrical car. And there is nothing to do when there is a fire of battery, just wait that is finished. It's also new training for the fireman for PV installation, autonomous PV installation or electrical car, to manage when there is a fire of a battery. Okay, really, so the fire, there is some precaution to take. So there is an international standard that said that you, so it's international, you have to be able to disconnect the generator to the inverter. And so it has to be able to be accessible from external part to cut it. So some example how we will proceed to design. So the more complicated is autonomous, because it is for autonomous installation that you have the, as I previously present, most of modularity, which is possible, most of components that are possible to design, and so you have to choose. So the methodology is first to identify the electrical energy which is required per day. Okay, so we will estimate that in kilowatt-hour per day. Usually, you have a security coefficient. Okay, you can measure by 20% this, you know, as a first rough approach to have an idea. Okay, you don't, if by any chance, if it is for a building and you had you plug your some smartphones and you didn't consider that on your estimation of energy, it's a bit stupid. So generally you measure this energy. You have to identify where you are, of course, and the estimation of the solar radiation that will arrive per month on the PV system. Okay, so in kilowatt-hour per square meter. Then, thanks to that, you will be able to size your PV central. Okay, that have to bring the energy which is required to per day. Okay. So at this stage, for the design of the PV central, you have several choices, as I told you. You can design it for just answering to your energy need, or to answer to energy need and to be able also to charge the battery at the same time. Okay, so if you oversize the PV, it could do both, charge the battery and use the energy as when there is sun. Okay. So you have to size the battery capacity. Okay. So to size the battery capacity is quite simple. It is the energy that you need per day, and you have to choose how many days of autonomy you want. Okay. Is it 1 day, 2 days, 3 days, 4 days, 5 days? How you could choose that? How can you choose 1, 2, 3, 4, 1 week?
But the requirement will be very, very high in your place, so the sun is not there.
Yes, so you have Now there is a lot of web meteorological data. So for sure, you have to go on internet and have a look on the specificity of the local climate. Summer and winter. In some area, for example, I imagine for the mousson, you will see that there is some days that there is no sun. So, of course, you will not take the whole period of the mousson, but investigate more locally what is the classical weather and how long you can have no sun. Of course, for example, in Europe, you can have 2 weeks without sun, so you will not put battery for 2 weeks because it will explode. But in some other country, you have enough sun, but you can see that sometimes or during 3 days there is no sun. So it's like this that you can guide yourself to select the autonomy. Okay. If it is also for a school or for a dwelling house. A school, for example, the weekend will not operate, so say, okay, we can take only 1 or 2 days of autonomy because the weekend are not included. There is not the night that is included also because if it is office building, you don't use too much electricity during the night, so the battery could be reduced. Okay. So many parameters that could help you to make a reasonable assumption regarding the number of days of autonomy. Then, so you go on the side of a PV array and select components. So module, inverter, battery, regulator, and so on, cable. Okay. It's like this that the tools are operating. Of course, each time you have to check the compatibility between the components. As I mentioned, the inverter has to be well designed relatively to the power of the central. If it is too oversized, of course, it will operate, but the accuracy to track the maximum power will not be so good, so you will lose some energy. And it's worse if it is smaller than the capacity of the production, because as soon as the power will be over the capacity of the inverter, it will disconnect. So when when he is not finding a maximum power, that means he is disconnecting. So your PV central is not injecting electricity anymore. Okay. So the inverter is a key element. All are key elements, but what is very important is to be consistent between each power, each intensity, in order to be fully compatible. For example, the modules, the field of modules, if at the born of the field of modules you have 48 volts, at the born of the extremity of the battery rack you have to have 48 volts. Okay, don't add 24 with 48 and so on. Okay, so here you have, for example, electrical energy required, so EG per day, average radiation, performance ratio. We will see more deeply what is it, but it is the global efficiency of the PV central. So that means that you have, assuming that you have a good selection of the cable, so in order to avoid Joule effect loss, well sizing of your PV installation, battery efficiency so of 80%. So it is related to the charge and discharge, 80% efficiency. Okay. So that means when you see 80% that there is also a MPP tracker. The depth of discharge, so 80%. So that means I'm going at the maximum which is advised for using the battery, 80% of discharge, and the number of day of autonomy. So the battery capacity is energy required. So as I told you, usually we identify clearly the energy, but we measure a little bit, so by 20%, or as a first approach. Multiply by the number of days of autonomy, divided by the depth of discharge. That means divided by the efficiency of the depth of discharge is to measure the capacity. Okay, if we divide by the depth of discharge of 80%, that means that we measure the capacity. Then the PV peak power is the energy which is something which PC so the power peak is the energy that you need divided by the performance ratio. So as I told you, performance ratio will focus more on it, but it is the global efficiency of the PV central. So you measure that, multiply by the efficiency of the battery, multiply by the irradiation. Okay. So take it because maybe I think there is an application after. I will ask you. So typically in Europe and in France, we will focus on the worst months, so winter months, where the daylight is smaller and when the weather is awful. To see the classical irradiation, okay? In some country where the irradiation is more or less constant, we can use the kind of mean annual irradiation as IGPG, okay? So for our installation, for example, in December, the days are the shorter. We will choose an inclined plane of 60 degrees south. 4 days of off-grid system, 2 days for off-grid system with diesel generators. So that means if you don't want to invest on 1 week of battery, which is very expensive, you can combine with another source, okay? If there is so much day without sun, you will not increase the number of battery. You will try to combine with another generation. So that's what I was showing to you, autonomous combined with electrical generator, diesel generator, even if it's not so good. Could be wind, depending on the area where you are. And now, as I told you, even we are looking at, even if it is connected to a grid, there are more and more often the addition of battery. Not because there is a grid cut very often in France, but because the price of electricity can change. And when there is a important need, it is the case during winter because there is heating system that are using electricity. The price is higher, So if you had some battery, you can charge the battery when the price is low and use the battery when the price is higher. Okay, so the autonomy is still the same when you, but you can combine with other source of energy regeneration in order to reduce the battery. Why it is 60 degrees of inclined plane? Because during winter time, the sunrise, we will see that this afternoon, is lower in the sky. Okay, so the more vertical you are, the better you are producing during winter time. Okay, so 60 is quite very well inclined because we are focusing on winter time to produce as much as possible electricity. If it is grid connected, we don't care about the inclination. We want to produce as much as possible to inject on the grid and to win money. Okay, so we don't care. It's around more 30 to 40 degrees because we want also to produce a lot during summertime. Okay, but during summertime we don't need so much electricity that. For autonomous, it is critical to have electricity. Okay, so that is the reason why that the inclination of your PV panels is also depending of the use you have. So 60 degrees is not optimum for summertime, whereas the days are bigger, but the sun is higher in the sky. So it's not an optimal inclination, but for autonomous installation, what is critical is to produce when you need and when there is a weak amount of energy. So it is winter. So that is the reason why it is 60 degrees and not 30 or 40 like if it was connected to the grid. Okay, so for example here we have a system with a small house or in the alpine space, for example, where you have some light, some TV with when you switch off without completely switch off. So there's the power and the number of time it is used for per day. For example, for the light, you consider that you will use the light 5 hours. The TV, you will show the TV 2 hours, and it's not good to switch on, switch off only like this because there is still a consumption of 10 watt during 22 hours. Usually, when you install a solar installation, you be careful not to have such consumption. Okay. So here you will have 120 watt of power per day. What is interesting is the energy, and so the total energy will be 542 watt hour. Okay, so the electrical energy required per day, it is 542. And so the capacity, if you estimate that you will have 12 volt, okay, at the board of your installation, the capacity will be the energy divided by the voltage, and you have 45 ampere hour. Okay. The maximum power which is required is 120 watt. So the maximum of intensity is 120 watt divided by the voltage, and it gives you the maximum of the intensity. So you see, it is 10 ampere, which is important in continuous. So it is the reason why that the design of the cable is very important also. Don't put any cables. It's very important to design it very well also, because the intensity could be high, and so if the cable is under design, it will hit a lot until they will have a fire, or it will melt, or could destroy. So the cable, we don't think too much about. We are thinking about PV battery, but the cable is very important also. If you have this intensity, you are able to design your cable. Okay. And you have also the inverter to use it. It's okay. So usually we don't take directly the electrical energy required per day like this. We measure a little bit to be sure. Okay. Is this clear? So I am going in south of France, but I can ask you here in Guwahati for the exam, be careful. So the need per day of my installation is estimated at 4 kilowatt-hour per day. So that means per year it's 1,460 kilowatt-hour per year. The global irradiation in a plane which is at 60 degrees, so Nice latitude is around 40 degrees. So the global irradiation is 2.84 kilowatt-hour per square meter per day in December. Okay. And the scale of the year is 1,592 kilowatt-hour per square meter per year. I said that I want 4 days, so it's ambitious, 4 days of autonomy. The performance ratio of my global installation is 80%. So that means that I have my global efficiency is 80%. The battery efficiency is 80%. The mass discharge battery is 80%. It's classical data regarding the battery that we take. So 80% it is because there is a MPP tracker. So the battery capacity will be 4 days, okay, multiplied by 4 kilowatt-hour per day, divided by 0.8, so the efficiency. I come back here, okay, energy required per day, number of days of autonomy divided the depth of the, not the efficiency, the depth of the discharge. Okay, and then after I have the peak power, which is energy required, divided by the performance ratio, the efficiency of the battery, and the irradiation per day. So capacity is 4 days with need of 4 kilowatt-hour per day divided by 0.8 charge use of the battery. I find 20 kilowatt-hour. So to reach 20 kilowatt-hour, as I told you, when I am at the extremity of my PV central, it's 12, 24, it could be 36, could be 48. It's this kind of multiple of 12, okay? Usually a panel, at the bottom of a panel, you have 12, 24, 48. So I can find that it could be 48 volt with a capacity of 416 ampere hour. Okay. For my peak power, so it is 4 the need divided by the performance ratio, 80%. There's almost everything is 80%. It's not easy to see. 80% of efficiency of the battery multiply by the global irradiation per day. Okay. So I will find in this configuration 2.2 kilowatt peak. Okay, so it's a small installation. I come back to my formula. So power peak is energy divided by the performance ratio, the efficiency of the battery, the irradiation per day. Usually, a conventional for a dwelling house connected to the grid, in France, you are not allowed to put under 3 kilowatt peak. Okay. So this is for autonomous installation. You do what you want. It is 2 kilowatt peak, but if it is grid connected in France, you are not allowed to go lower than 3 kilowatt peak. Okay, so the annual production used will be about 1,460 kWh per year. The photovoltaic generation will be 2.2 kilowatt peak multiplied by the mean global irradiation per year. So it's 1,592 kilowatt-hour per square meter per year, multiplied by the performance ratio. So you will generate 2,802 kilowatt-hour per year. Okay. Is it okay, or you have some question? So it is a roof design. Of course, you have also to identify if in the surrounding of your installation you have no shadow, okay? Because data that are provided on the global irradiation on the inclined plane of 60 degrees and the wool, the global energy received on this plane for the year, it is without shadow. So it's very important to be able to identify in your surrounding if you have a close shadow or mountainous area that could modify that. Okay. Regarding the standards, so for PV modules you have a lot of different standards depending of the country. Each country gives some standard to be sure. It is necessary for the insurance to have some standards, because if one of the component is not referenced in a standards, it could have problem after if there's fire or problem of damage. So there is standard for PV modules, for inverter, for battery, for cables also. Cables is very important to take some cables dedicated for solar, because they are submitted to high intensity and also to UV because it's outdoor, and so they are aging very fastly. A part of important thing is LCA, so life cycle analysis. As I previously mentioned when I was speaking about the production of PV modules, there was some critics about the amount of energy which is necessary to produce PV panels. As I previously said, you have to use a furnace where you will generate the silicon. Okay, this furnace is over 1000 degrees to allow to melt the silicon. Then you have to cut. Then you have to treat. Then you have to put some silver, and then you have to put all the sail on the glass with resin. You have to heat again to make the resin encapsulate the so there was some criticism, and there is still some. So we have demonstrated that finally during his life, a PV modules produce more energy that is necessary to manufacture it. But there is still some critics, and it's justified about what we do after the life of the PV. Okay, is it possible to recover a part of the material? We see for example that for the wafer is not possible because the silicon has been treated with bore and phosphor with anti-reflective coating. There is also some resin that is in the surrounding, so it's not so easy. So there is more and more study on life cycle analysis and recyclability of PV. So there is an European directive that to use the material for the same purpose, of course. So is not to use the glass to rebuild some PV modules, to use cells to rebuild PV modules, and so on. So silicon, in terms of material resource, there is silicon on Earth, so it's not really a problem. Silver is more delicate. So silver is to collect the electron at the surface of a wafer. Okay, you have around 0.12 gram for watt peak for a panel. So you have some silver and could be expensive. It's becoming rare since 2021. You have some tellurium sometimes at a very low concentration. You have 0.01 ppm, but it is a rare earth. You have also some indium, also at very low concentration, but it is also considered as a rare earth. For the battery, so for lead, you have it's 70% of the battery on the market. Lead also is becoming rare. Lithium is rare also, is used everywhere. So the reserve is not so huge. So in terms of resource, is more delicate at the cell level regarding silver, and at the battery level regarding, yes, the main components of the materials. And it is more and more used for electrical car and so. You can have also for some PV technology cadmium tellurium, arsenic of gallium, dangerous materials, of course, dangerous for environment. Silicon is not dangerous, but cadmium tellurium and arsenic of gallium is toxic materials. So regarding the energy payback, we have had a huge improvement. Okay, compared to the beginning of the manufacture of PV panels, where the energy payback, so on the vertical axis, it is the number of years. Okay, so you can see that in the middle of the 70s, the energy payback for the PV panels was around 20 years. So at that time, it means that yes, PV panels were producing just a bit more than the amount of energy that was used to manufacture. Why? Because the efficiency of the cell were very low, okay, and the process of manufacture the PV panels were closely the same as now, okay. Whereas now, since 2010, we have reached a very low level. The energy payback due to the increase of efficiency of the cells, mainly that, the increase of efficiency of the cells, the energy payback time in number of years has considerably been reduced, and it is 1 or 2 years. Okay, after 1 or 2 years of operating, a PV panels reimburse the energy that has been required to manufacture it. Energy for which is necessary for manufacturing these PV modules, so classical monocrystalline or polycrystalline is around 500 kilowatt hour per square meter. Okay, so that means that for watt peak, per watt peak, it is around 4 kilowatt hour per watt peak. The energy payback time is around 3 or 4 years. Okay. For amorphous silicon, it is shorter. It's 2 years, but the performance are less important. For cadmium tellurium, the energy which is required to manufacture is around 130 kilowatt hour per square meter, which is lower than classical silicon, and the energy payback time is around 1.3 years. Cadmium tellurium is quite efficient, but yes, there is some toxic materials, and it's a rare earth also, rare materials. So in terms of emission of CO2 for the different, if we compare, because if you want to make a life cycle analysis of solar PV, we have also to compare to the other way to produce. So emission of CO2 per kilowatt hour, which is produced by hydroelectricity, is 4 kilowatt hour per gram of CO2. For nuclear is 6. Okay. For wind, could be very large scales, between 3 to 22 emission of CO2 per kilowatt hour. And for photovoltaic is 60 to 150. Okay. Why such level? You can see it's not very good compared to hydroelectricity, nuclear. Hmm? No. Hmm? No.
Maybe France nuclear more focus is there because of the France it is low.
No, yes, nuclear generate a low level of CO2 per kilowatt hour, but more than hydroelectricity. Why for photovoltaic it's higher than this kind of resource? Hmm?
Lifetime.
No, it's not lifetime. The question is why to produce the equivalent of 1 kilowatt hour of photovoltaic, the CO2 content finally is between 60 to 150. Whereas, no. So it's not.
Manufacturing of solar cells.
Yes, it is manufacturing. And why so high? Because it's manufactured mainly in China. And at that time, China is still using a lot of coal to generate electricity to then manufacture PV and PV panels. Okay, that means that the use of energy for PV module manufacture is very high in CO2 content because of the energy source which is used to manufacture them. Okay, if China continue to develop PV such as now, it's more than 80% of the production of the PV in the world is in China. If it was changing by using electricity from dam, nuclear, and wind turbine, for example, this weight of CO2 will decrease. Okay, but it is energy which is used to manufacture that is important, is very carbonate at the time, still carbonate. Okay. And then after you have use of classical over, which is carbonate, but because it is gas, petrol, and thing. But
That's why I wrote 16 in Germany and 870 in China.
sorry. Sorry.
Average for countries in France is 90 gram.
Yes.
Then 16 in Germany.
Yes. 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 That's yes. Yes, sorry, I did not say. So yes, in France, because it's mainly nuclear, so the content is lower. In Germany, because they were still using gas, but now I think it will decrease because there are more and more wind and solar energy. And in China is important due to the use of the back field resource, which is coal. Yeah. Okay. So, but this has to be included in the weight of the PV panels. As well, if you put a PV panel which has been manufactured in China, plus imported in Europe, there is a transportation also. Except if you are using hydrogen boat, for example, it will be also a cost in terms of CO2. So it's not, yes, so it's pushed to produce locally, to use locally, and to produce with clean energy, of course, because the content, otherwise the content, even if it's a green energy at the end, the content to produce it is not so good in terms of CO2. Okay. How to recycle it now? So there is different way. Okay. So this way, so you will have to take the panels, usually on the surrounding of the panels, you have a frame in aluminium. So you will take out the aluminium frame. So after you go to backsheet removal, then you go to EVA burning. So it's a problem because EVA is here to encapsulate the cells and to be fully waterproof during the lifetime of the PV panels. So EVA is everywhere. Okay, you put a slide of EVA, you have heated the EVA, and the EVA melt and encapsulate perfectly the PV cells. So even if you want to heat the PV panels to try to separate the backsheet and the cells, of course the EVA will become a kind of viscous element, but you will never have a clean surface of the glass, clean surface of the PV cells. You will separate, but you will have EVA everywhere. So the only way, if you want to recover the materials, is to burn it, or maybe to use, I don't know, acid or chemical reaction to dissolve the EVA. But at that time, it's going and it's burned. Okay. Then the glass and the cells are separate. Okay. And you can after recover the silicon cell fragment. The glass is also broken because the glass is I don't remember. We can trumpet glass. It's very strong glass that been specially manufactured to resist to shock. So it is a very hard glass. It has been specially treated for that. It's like for the car, okay? But if you have a strong impact that will destroy the glass, it will explode in multi-piece, okay? So you can't cut such a glass. You can't take this glass and say, I will cut to make another glass or things like this. It is specialized trumpet heated treated glass that is not cuttable and only destroyed in small pieces, like a car. So you will have small cullet of glass, and then you can, in the other side, recover all the metals, especially the silver. Okay. So it is a more clean way actually to recycle the PV. What is about the silicon cell fragment? You can't use it anymore for PV production. As I told you, there was too much treatment, chemical treatment, mixed with silver. So the purity, for sure, even if for PV manufacture you need less pure silicon, it's not usable for PV. Okay. So you have the percentage in terms of composition. You have 78% of glass, 10% of the aluminium, which is mainly for the frame of the PV, 7% of the plastic, so EVA, and 5% of metals and semiconductors. So it's very light. Silver is very light and silicon is very light. Do you have some remark for this? So I have one remark. It is to remove the frame is okay. To remove the backsheet is not so okay. You have to heat you have to heat the modules because you have glass, resin, cells, and backsheet. And the backsheet is glued with the resin. Okay, so if you want to separate the backsheet, which is generally a Tedlar, you have to heat a bit. Okay, it's less delicate to separate with the glass because it's Teflon. Sorry, because it's easy, but you have still to warm a bit. So here, to separate the backsheet, you have to warm. Then here, you have to burn. So that means you have consuming energy also. Okay, and to separate the glass, so you have to inject energy at least 2 stages to recover, to recycle it. So that means if you are considering the whole life cycle analysis, you have to include also in the energy payback time the manufacturer of PV, but also the recycling of the PV. This is a part of energy which is also included in the energy content. Okay. I've made something wrong or no? It's okay. I think it's not full screen, but okay. There is another way to recycling, which is not a real recycling. The other way is to take the panels, get rid of the aluminum frame, but then after to break it in a very small piece and to use it to as a underground layer for road, for example. Okay, for building some road, it is used as a kind of granular that is under, so it's to hide it. But it's not real recycling, but it's also the second way. This is more the complete recycling way. The other way is to break the PV panels in a small pieces and to use it for road construction. Or to put, we can put everything also in the concrete. There is some try to use it as a material of construction, okay. An interesting study showed that in urban area, when we want to massively integrate solar PV, in some country you can reach around 45% of the energy need, managing the production at the scale of a big territory, and in US more, only on building integration. And why in US more? Because big house, there's a lot of availability in surface integration, and so this shows that. As I previously, and there was yesterday an interesting question. Okay, there is a lot of study to try to see how we can manage the production, maximum of production of energy where the energy needs are, so in the cities, and how to manage the flexibility of this. But there is also study working on the impact of such a massive integration at the city scale on urban climate. And it's not still fully identified. What are parameters that are interesting? It is, it's a mix between English and French. Energy yield ratio and energy payback ratio. So here you have some different technology, and so the energy payback is continuously decreasing because of the efficiency of the modules, but you have also yes, full screen. Yes, thank you. To consider the lifetime, okay. So here it is a study for 20 years of lifetime or 30 years of lifetime, and yes. So for the different technology, of course, the energy yield ratio is good for country like Australia. Northern Europe a little bit less, and depending of the way to integrate, is it grid connected rooftop system or is it solar home system? You have also different energy yield ratio. Okay, so it is yes, energy payback. So this is important also to consider in the life cycle analysis. So here, sorry, it is in French. For Paris, Lyon and Marseille, so Paris is in north of France, Lyon middle, and Marseille south. So the radiation are higher in Marseille per year than in Paris, than in Lyon. So you see, more you are going in the south, more the global radiation is higher. There was some study if you integrate as a roof, so the toit, the facade, depending of these cities, and what could be expected. Of course, when you are integrate in a facade, you can see that, for example, for Paris, the energy payback time in terms of years is higher. If you integrate your PV central on a facade in Paris, the energy payback time will be around 4 years. Okay. Whereas if you integrate on the roof, the inclination is more optimized. You have around 3 years. But why the facade are studied? Because the facade in a city represents the more the biggest potential of integration of solar energy. When you have big tower, the roof is very limited compared to the facade. So the energy payback time is higher in terms of year than you are in facade. For Lyon, for example, when you integrate in a facade, you will have energy payback time 4 years, whereas in a roof it will be 2.6 years, and in Marseille it could be interesting and very to use it as in a facade or on a roof. So you have 3 years of energy payback time when it is vertical, 80 degrees inclination, and around 2 when it is on the roof. Of course, so in the life cycle analysis, it depends of the way you integrate it to the building also. Okay. Do you have any question regarding this part? So this afternoon we will do a tutorial regarding the design of a PV central. You will work a bit, and now I just finished for the performance ratio. I spoke about the performance ratio on the design, so I will show you this. No, oui, je regardais là. Yes, to open a document. Performance assessment. Yes. Thank you. Oh. Okay, thank you. Okay, so usually the one thing which is important, it is when you are producing electricity, very often the classical curve of the production along the day is like this, like a Gaussian, okay? Why classically? Because we put at the south if we are in the north hemisphere, or in the north if we are in the south hemisphere, and we try to produce as much as possible. So that means the morning we start to produce, and at midday, at time solar through, we are producing the maximum. Now, and so that oblige for the other part to adapt, to answer when there is no sun, and to manage this overproduction compared to the need. Okay? So now, as I was previously said, that we are investigating to integrate on the facade, which is not optimal inclination, but also to integrate in east and west, okay, to better fit with the need and to have a better flexibility. Because in Europe, where now there is one turbine, solar energy, it's become more and more often a problem during summertime when it is very sunny day and windy day. There is too much production of electricity, and everybody try to give it to a neighbor. Germany, for example, sometimes inject in Slovakia. I was obliged because otherwise I was risking a blackout of my system. So you see that, okay, it was always led by the economic gain to produce as much as possible, but now we try also to produce when we need it. So east and west orientation have sense, because the morning, usually the people, when they are at home, they consume energy the morning, sometimes the midday when they come back, and the evening. Okay, so east and west have an interest. So in more and more try to manage the flexibility at the scale of a big territory, saying that in a city we can admit that the morning some buildings are fully in the sun and will produce energy. Then after they will be in the shadow of the neighbor, but the other building will be in the sun and will produce energy. So you can imagine to have almost a constant production all over the day, playing with the variability of the sun at the city scale, even if some buildings start to produce and then stop. Okay, so at that time, of course, it is a concept, but it become more and more a reality regarding the flexibility of the grid. Okay. So I've already spoke about that, about the mismatch, but what is important, I want to show you. So this is a PV central which we are working a lot on. It is in Djibouti with one of my previous PhD students. We are investigating the production, the performance ratio, the impact of the soiling on the PV panels. Of course, there is some times where there is a lot of sun coming from the desert. There is some times where there is some rain. There is sometimes where there is some specific wind, which is, we are looking also at the impact of the wind on that to identify classical performance ratio, but also other parameters that can modify the performance of the PV central.
Like people is there in the rooftop. The pebbles, small pebbles.
It's not on the rooftop, no?
It's the rooftop.
Ah, no, it's not a rooftop. It's a big central, not on a rooftop. You can see the building, so it's on the ground. And the inclination is very small because the latitude in Djibouti is around 10 degrees. Inclination is 10 degrees here. So it's very a problem for the dust because it's not horizontal but almost. So dust can stay long time, whereas when it is more inclined. And so there's many parameters that we are studying it. Okay, so for the performance assessment, so there is reference yield, so what is expected, okay, when you are designing your PV central, you are expecting a reference yield, but you are losing some energy due to the array, the cables. You have then the array yield, and you have over global loss, so that could be linked to the temperature, which is not well known at the time. It is a soiling. What is the soiling layer will impact very strongly the performance. So the main difference between what you expect and what you really have, okay, the ratio of that is a performance ratio. But finally, you can see that it is a kind of a global efficiency, okay? And it is a very interesting parameter. A good performance ratio, that means it's give an idea of the operating condition of your central to see if it is comfortable or not. So if the central is operating well, in a good condition, quite comfortable, it is 80%, okay? If you are under 80%, that means that there is a problem. A problem that you can resolve, or a problem which could be linked to environmental parameters, okay? Typically, temperature, okay? So if you are under 80%, if in principle when you look at your PV central, all the PV seems to be good, you can have a drone and have a view of infrared with an infrared camera, no hotspot, everything seems to be okay and so on. It is the temperature, because maybe it's too hot outside, and so under 80 is temperature. It could be linked also because the PV central is not well designed at the beginning. If you put on a roof, if the installer puts the PV panel directly on the insulation, for example, you will go at a higher level of temperature during summertime, and the performance ratio will decrease. Okay, so it's a way also to see if your central has been well installed, because between design and reality there's also the installation. Okay, and if you are all the time under 80%, there is a problem. If your panel seems to be okay, if, there is a problem. So it's a very good indicator of the health of the PV central. But also that means that this indicator is varying all the time, okay? And usually we analyze it per month. We estimate the performance ratio per month that we will do that Friday. So do you think that the performance ratio is better in summer or in winter? No. Is bad. Because the paradox is that during summertime, as the days are longer and the days are sunny, your central will produce more, for sure. Okay. But the performance ratio, when you compare to the winter, will be lower, will be worse than winter because the temperature is higher. And so usually you will find that in summer you don't care about the performance ratio because your central is producing and so on. But when you look at the performance ratio, you will see that it is worse. Whereas in winter, in winter, the main problem of the production is that the days are shorter. Whereas if the day was as long as in summer, the production will be much better because the performance ratio is better. You have also other indicators like reference yield. So the reference yield is the ratio between the solar radiation arriving at the surface and the quantity of the reference radiation. So it is, our reference radiation is 1000 watt per square meter. This parameter represents the number of hours during which the irradiation is equal to that of reference. Okay. In some countries, never reach. Okay. So it is, does my central operate sometimes at the reference radiation? I remind you that the reference radiation is 1000 watt per square meter and reference temperature 25. Okay, so of course when it is lower than 1000, it will not produce what is expected when you are looking at the peak power. Okay, so this is an indicator. It could be in terms of hours. So it could be 0. It's not bad linked to the PV central. It is linked to the environment. Okay. You have also the array yield. So this is the PV is defined by the ratio between the total energy generated. So it's an energy, it's not a power anymore, by the PV arrays for a defined period. So it could be day, month, year. And the nominal power of the array under standard conditions. So standard conditions is 1000 watt per square meter, 25 degrees. And spectrum air mass 1.5. Okay, so it could be also in terms of hour. I suggest to have a month indicator because the year, if you have two different operating conditions between summer and winter, is reduced. It's better to reason between summer, winter, and months is good. We will see that for the performance ratio. You have also the final yield. So the final yield corresponds to the total energy produced by the PV system. So it's also energy divided by the nominal installed DC power. So in a power peak, this quantity represents the number of hours. So energy divided by power is time of a PV array should operate at its rated power. Okay, so this normalizes the energy produced with respect to the size of the system. It gives you an idea if you have well-sized system or not, finally. Okay, it's not so often used, but it's an indicator of the well operating of your PV central. Well or bad could be linked to the PV central or could be linked to the environment. Okay, that means a very polluted environment, very hot environment, no wind in the environment, some shadow. Okay, some shadow. If you have some shadow, it's not the fault of your PV central. It is the surrounding. It may be the fault of the designer. And the performance ratio, yes, it's a global idea of the operating condition of the PV central, and also it could have some consequences on the design on the installation of this PV central. This performance ratio so indicates the overall effect of loss. So it's included all kind of loss. Generally, we consider the inverter, the cable, the temperature effect, okay? But there is more effect that we try to integrate in the performance ratio. And as I told you, if it is around 80% or 0.8, it's good. No worries about your PV central. That means it's operating quite a convenable conditions, and it's good. If it is under all the time under 80%, there is a problem. Okay, 70% is a big problem. 75 is not good. So 75 could link only to the temperature. 70% that not only the temperature, there's something else. And if you are lower, that's a big trouble. Okay, even if you are producing electricity, it's important to see that. The system loss, of course, so it is different between the PV array yield and the final yield. Could be hours also. The capture loss, so the represent the loss due to the module temperature, the wiring, the cable, as I told, partial shading, spectral loss, soiling. So it's when you have a performance ratio which is under 80, under 75%, you should investigate this indicator to see what could be the reason. Is it in your PV central? And the array efficiency. So the array efficiency is the efficiency of the photovoltaic field, and it is the ratio between the total energy generated by the PV array to the amount of irradiation on the plane and the area of photovoltaic yields. So it gives you, yes, just focusing on the PV array like a PV panel, like a PV cell. Okay, just focusing on the PV. Well, there's other indicators. I will not go deeply on all these indicators, but it is all the indicators that we are using to identify the origin of a decrease of performance or abnormal performance that allow to give some indication. Okay, so the global data here. So you have solar radiation, the PV array. So the PV array is only the PV central. Then you have the inverter, you have the grid, and so for at the beginning you have the reference yield. So then you have the array yield due to the efficiency of this PV central, and you have the final yield, and the global ratio between what you have at the end and what you have at the beginning give you the performance ratio finally, which is integrating all of these parameters. If there is a bad performance ratio, that means that there is a problem on one stage of this. So after you go deeply in the different indicator to try to identify the origin of this bad performance ratio. Okay, we will in the application mainly focus on the global performance ratio, not on all these indicators, but it's good to know that performance ratio is a global estimation of the good or bad or comfort of our PV central. If there is a problem, you could investigate at each level the indicator to see where is the problem. Okay? It is the concept. Do you have any question on this? I think we can stop here. And then, so this afternoon is tutorial part. Maybe, I don't know how, well, no, I will, for the tutorial part, I will work on this. Okay?
Conclude here.
Yes?
So we'll next we'll meet at 3 o'clock. So please occupy before 10 minutes, so that we can start at 3 o'clock.
Okay.
For doing, it takes time to complete the thing.
Yes.
Thank you very much.
So at 3 we start again.
Come here and drop you.
Yes? Good. Aye.
sometime.
Ah.
And then you take this one, and then paint it. Now it is ready to write.
Okay. I will try. Good.
Of the GIAN course. I don't know why participants are not here. So we are expecting that participants should be here by maybe 2:50. Anyway, we can start our schedule tutorial.
Okay.
Okay. So floor is yours.
So the first one is dedicated to exergy and energy evaluation of solar hybrid photovoltaic thermal collector, and especially also with phase change materials. Why is it a good example of using exergy? Is because we have two kinds of energy. It's the same unit, but it's not the same content. Okay. With electricity, you can do what you want. You can heat, even you can heat a boiler, just injecting the electricity by a resistance. Okay. You can cool, couple with a cooling machine. You can have light. You can do what you want. So the content of 1 watt of electricity is different of 1 watt of thermal energy. Thermal energy can have also a good potential if the temperature is at a certain level. We have seen that we are able to generate what we want if we concentrate the solar energy and if we reach a temperature over 200, 300, so we are able to generate steam. Then from the steam we are able to generate electricity, or we can generate heat, we can generate cool. We will see in the lecture about solar heating and cooling. Okay, so the content is not the same. So if we want to, if we have a system which is doing both, we should be able to add a kind of unit, so to clearly highlight what is the energy potential of this component, which is mixing thermal and electricity. So it is exergy. We will see that later. So the origin of PVT, I already show you the spectral solar spectrum. After he is crossing the atmosphere, so you see some hole here due to H2, so absorption. You have also azote absorption and CO2 absorption, and so on. Okay, so the first is say, okay, the only part which is useful for PV is in short wavelengths, and most of the energy coming from the sun, so around 80%, is not enhanced, is not used. Okay, so is it possible to try to use a part of that using the PV collector as a collector also for thermal? Okay, so it's the first thing. So there is different family of hybrid photovoltaic thermal collector with air, with water, covered or not, with also concentration. This is an example of concentration CPV. Here you have the PV cell, okay, and you have concentration of solar radiation on this focal. So at that stage you are also collecting solar energy for PV conversion, and also at the back side thermal energy that could reach for such components more than 100 degrees. It could be oil, for example. Okay. This is, we can see it seems to be a PV function, uncovered, okay, because we don't see a glass over the PV module, so it looks like uncovered hybrid photovoltaic thermal collector, probably with water, because uncovered can't reach high level of temperature, okay. With air, there is different, you can find in the literature different way. So you can have a glass cover, and at the absorber level layer of PV cells, okay. And so the air Just a disconnection. So the radiation is crossing the glass, go to the cell, a part is converted in electricity, and the other part is recovered as thermal energy on air. So on Q, M, C, P, delta T, T out, moins T out. So it's allowed to hit the air. As it is glass covered, you can reach 50, 60 degrees on air, okay? So it could be for drying, for example, when you need some heat on air. So it could be useful for drying and so on. Other solution is to have the PV as a cover, okay? So a semi-transparent PV that allow in some part to leave the radiation crossing and the part which is absorbed, converted in electricity. So finally you could be heated in both sides, but in this configuration the level of temperature is lower than here. Okay, you have other configuration, double flux, one at the upper face or the out face, or to increase the path of the air and in a loop at the which is the case, for example, with evacuate tube water. With water, you can have a circulation like this around the absorber. Okay, so it is with air, which is the more simplest way to recover a part of it. But of course, the heat mass of the air is less efficient than heat mass of water, so you are recovering less. So example. So this is an example also that we have developed in the past on a project where the principle was to have an operating principle during the summertime. Okay, so during summertime it is a double skin with PV envelope. Okay, this is PV. And so during summertime you use this PV envelope as an absorber.
So what is the objective here?
To heat, and so you try to develop the natural ventilation by chimney effect. Like this, you generate a free cooling of the PV envelope, and you can also use this kind of natural ventilation for ventilated inside the building. Here you have the north, here you have the south. Okay, so the cool air is in north where there is no sun and cross. Okay, during the winter time we want to use it as a solar hybrid photovoltaic thermal collector. So it is closed. There is close and so we recover a part of the preheating of air with circulation. So it's a kind of trombe wall. Developed in the 1970s, something like this. Okay, so you collect, so you use it to operating the air of the thing. So it's mechanical, of course. Here you have obliged to ventilate, whereas here it's natural convection. So this is an example of BIPV-T or BIPV with T. So this is what we have achieved for, so it is experimental dwelling house. So it is double skin PV facade. As I showed you yesterday, we were playing also with the color of the sails, just playing with the anti-reflective coating. So changing the width of this anti-reflecting coating. You can notice also that there is a difference of density of sail for some modules. So not here, it's fully opaque, but here. The principle is to leave some light going inside the house and to concentrate the sail when there is solar spot in summertime. So it is to protect the building to overheat. Thanks to this protection, we have modelized the solar radiation path, and at the place where during summertime there was a more concentration of solar energy, we put more cells to protect. Okay. But for this kind of configuration, in terms of inverter, if you have followed my lecture this morning, what you have to do, is it one inverter for the whole installation? Is it one inverter for the roof and one inverter for the facade? What you will do?
Inverter cost is also very high.
Yes, the cost is very high.
We need to check with this.
So you can have one inverter for that, okay? Seems to be uniform, opaque, and so on. But for this, it's a kind of mismatch, because each module has a different power, okay? So it looks like if in some modules there is shadow, because there is no cell, okay? So for this, you are obliged to put one microinverter per panel, okay? Because otherwise it will be completely randomly. So for this configuration, it was the beginning of the microinverter. So there was one microinverter per module, because there was such a difference of power between modules that it was impossible to manage. Okay. So for this, for sure, when you see that there is one microinverter per module, this could be one inverter for the whole. And even if it was uniform here, okay, even if it was uniform here and uniform here, you are at least obliged to have two inverters, because even if it is the same panel here and the same panel here, the inclination is different. So they will operate in a different condition, okay? So you can't put, even if it was fully uniform, you can't put only one inverter for the whole installation. You have at least to have one inverter for this part and one inverter for the roof, okay? It's a double inclination. We have developed also other hybrid photovoltaic thermal with water. So the first attempt was a long time ago with glass covered. We bought a solar thermal with copper heat exchanger. And so we put some conductive past and put the solar PV and then a glass cover. It was not so good at the time, but we could reach, in terms of efficiency in electricity, between 10 and 15%. The more accurate that we have developed, it is this one. It has been developed with EDF and the Fraunhofer Institute. It is a glass cover PV-T. So finally, the configuration is like this. plus a cover. Okay. The innovation is that the PV cell were directly put on the heat exchanger. So there was no backsheet, only a thin film in order to protect the cell from water, but no, so it was directly put on this. So it was quite efficient, but it is glass cover. So for this kind of PVT, you are obliged to manage the production of hot water. That means that we were able to reach 80 degrees with domestic hot water. We could reach 85 degrees. Okay? So that means that if you reach with water 85 degrees, you reach with your cell not far from 85 degrees. So it's not good for the PV function. Okay? At the beginning, there was a lot of damage because there was dilatation. Some cells were cracking. The silver part was sometimes also cracking and so on. So for such a collector, you have to manage few hours in the day to produce hot water for domestic hot water. And then you have to give the priority to electricity. So that means to have to use the water to cool and not to increase in temperature. Okay. It is the reason why that you don't really find industrial application of such components, because it is too dangerous for industry to sell such a kind of covered hybrid PVT, because in terms of warranty, insurance, you can imagine that if the temperature is growing too much, for example, when people are going in holidays, they don't use hot water, the temperature could increase and destroy completely the PV function. Okay? And even in time, in terms of aging, if one time per day you reach 85 degrees for 2 hours, it's not really good for the PV function. Okay, so this is the reason why that it was very efficient, but very hard to manage, and difficult to find in industrial level, because in terms of warranty of performance in time could be.
In the life of the PV cells.
Yes, of the PV function, and all the PV connection don't like too much. So we also work with this company, which is PolySun, which manufacture industrially in France PVT uncovered. Okay, so the principle of a heat exchanger were more or less the same without cover, and so then they were selling that for heat pump couplings, heating the swimming pool. It's still it is the case. Okay. So yes, the experiments that we have done also at EDF with this, it was to couple the PVT with tank and to manage, to find scenario of managing the production of hot water during the day. So to fill the tank in terms of solar thermal during 2 hours, it was enough, and then to make the water used for cooling. So no connection to the tank anymore, and to cool the PVT in order to increase the efficiency of PV. Okay, we have also worked with Ankita on hybrid PVT application, more theoretically, adding some phase change materials. So the principle was to have PV cells and then add water channel, try to find good heat exchanger, and also to add a layer of phase change materials. So we have found that the addition of phase change materials is quite interesting for kind of using this as a dump. We can say that dump to stabilize the hot water production. Also to decrease a little bit the temperature sometimes and to increase the efficiency of PV modules. We work on water and also with air, and there was a paper made on this exploitation with classical electrical analogy modeling, but no confrontation with experimentation. Okay, a more recent one, so to see that there is still research on this in 2020, and it is in Indian, which has developed PVT with phase change materials and have analyzed by experimental and modeling. Okay. So this is two PVT. So there is one PVT with water, one PVT plus phase change materials. The phase change materials, he has chosen a temperature around 35 degrees. Could be 30. It depends on the ambient operating condition. And so he has compared. He has worked also on heat exchanger. As you can see, the heat exchanger, he said that it is look like a butterfly wing. I'm not fully convinced of the heat exchanger, but about the improvement of the wool collector, yes. Okay. Because you see the heat exchanger is like this. Like this, and this is going like this, and like this also, and this is going like this, thing like it looks like something. So you can see here the shape. So for such device, and as we have done also in the past, as I mentioned, you are obliged to compare what is comparable. Thermal energy is not directly comparable to electrical energy. Even if the units are the same, you have to evaluate the content, the quality of this energy. You remember yesterday when Pankaj was giving some information about solar thermal efficiency. If you plot the solar thermal efficiency of collector, you will see that it is the efficiency here, sorry. It depends of a ratio depending of the water temperature minus the ambient temperature. Okay, so for a flat plate uncovered collector, you have a good efficiency finally when the water temperature is close from the ambient temperature, because it's a ratio. Okay, so this is becoming big. Temperature of water minus the ambient temperature is becoming big as a ratio when the water is close to the ambient. But we have no use of water temperature which is at the ambient temperature. Okay, so that means that yes, of course, a flat plate uncovered has a good efficiency when the water temperature is going to near the ambient temperature compared to the other that will be like this. A coverhead will be like this, for example. but we are not interested by when the water of temperature is becoming close of the ambient temperature. That means that we don't give input in terms of thermal energy. Okay, so we are obliged to compare, and it is the reason why we are using exergy. So in an energy point of view, we can say that we can add the efficiency of thermal plus efficiency of electrical. The power which is maximum generate, as you remember, the fill factor is equal to voltage for which the power is maximum multiplied by the intensity for which the power is maximal, and divided by the intensity in open circuit. No, sorry, not in open circuit. Oh, in short circuit. Short circuit and voltage in open circuit. Okay, so that means that the power max which is generated for maximum voltage multiplied by intensity maximum, it is that. Okay, and so exergy allow to make a comparison between both. It allows also to be interesting to see if there is a lack of exergy or not in your system. Okay, so it is this which is well seen and well used to when you have a system which is generate both two different energy vectors finally. Here it's electricity and thermal. Okay. So you can add exergy, thermal exergy, and electrical exergy. Thermal. Okay. And so I will give you a numerical application in order to have an idea of the value. Okay, so for thermal, what is a typical so I'm going too fast. So here, Q is energy. Huh? It's here, Q. MCP, so mass flow rate. So we will take a volumic mass flow rate of 1. In the paper, he tested 1 liter per minute to 4 liter per minute. What we can take as ambient temperature, we can take around 25 degrees. It's 25 degrees. Yes, it's a hieroglyph. And a typical, so water temperature, we can say in the collector, we can take 60 degrees. with 25 degree outside, that means it could be around summertime. It could be possible. It's a bit high, maybe if it is uncovered. But we can reach, yes, between 50 and 60 degrees. Okay. So I would like to have the thermal exergy, please. And then we will evaluate the electrical exergy. So this is water. In principle, it is outlet temperature, but sometimes we can take the mean temperature inside the collector. So I will say it is outlet. So as soon as you have a value, you give it to me. Maybe you want me to remind you that Cp is cat dot 186 kilojoule per kilogramme per Kelvin. So the exergy has been extracted from the second principle of thermodynamics. So to achieve this kind of formula, you...
What is the temperature difference?
Sorry?
What temperature difference? What is before the previous slide?
So I said TA is 25. And I say that I will consider that T water is around 60.
T water is the outlet temperature.
Yes, it's in principle is the outlet temperature. I just compute it between at midday, so I hope I have no mistake. With electrical, this is the area of the collector or the PV. This is irradiation. So typically we can say that for such a good day, the irradiation could be 800 or 900, okay?
TS is surface temperature of the sun.
Hmm?
TS,
Where?
the second expression.
Ah, yes, here it is evaluation of the surface temperature. Yes. So what you will consider as a TS, for example?
6,000.
Hmm?
6,000.
Yes. I'm going to check that. I'm not sure.
How much mass we are considering? 2 liter, 3 liter per minute?
What I said, I have made my for 1 liter per minute.
1 liter. MCPDT. CP is known. Delta P is known. 60 minus 25. 60 minus 25. 1 liter per minute. 1 liter is 20 minus 3. 20 minus 3 will be 60. We need to convert LPM to kg per second. Of course.
You are obliged to use international. Yes, yes, every time.
Who did the result? Don't ask this to the police. Do one by one. I'm an exergy related. What is NC?
It is a number of modules, but we will consider one. Okay. No, and so what you will consider for TS?
6,000
Ah no, it is not the. What did you take for TS?
Sun temperature.
Ah no, it's not sun. It is surface of the module. Surface temperature of the modules, which is in fact usually the temperature of the surface of the cells, but because if you took the temperature of the sun, it's all the time negligible. So it's a
It will be very less only.
panel.
1 minus something. If value is always 1 minus something, it will be very less only.
Hmm?
Always 1 minus something.
Ah yes.
It will be very less only always.
Yes, we've got to check. We will say. I didn't compute it that. So if we consider ambient temperature, sorry, what I said for the ambient temperature, 25. So ambient temperature is 3 Kelvin. Yes. No, it's not free, free, free. Free, free, free is, sorry, the water temperature. Wait, you imagine 298 Kelvin. So do you have a value for thermal exergy?
Exergy thermal, how much? It's very simple to calculate.
So
Someone got 351 total.
the total exergy? Hmm?
She got 351.
51? I don't find that. Which is your unit? Watt? Or kilowatt?
MCP decreased.
Kilowatt?
2 point something, 2.44 kilowatt.
Maybe, yes. I didn't have the electrical one. Can you give the thermal one? I got the thermal one. Maybe first you can give me this energy.
2.4.
Yes, 2.4. Me, 4.5 or 4.9 you said?
490.
4.9, okay. Okay. So if you leave it like this, you should find around 0.26 kilowatt or 0.2 something. mistake. I have to check. So do you find the thermal around 0.26 or?
268.
Here? So 0.2?
685.
Okay. Yes, kilowatt. And I have a doubt about this. Oh, you have right. No, you are right. It is sun for this because we can find two formula. One like the thermal. So instead of useful energy, it is electrical energy, and one with the sun. I put it here. No. No, no, no. I thought I was put the. Sorry. I thought I put that. So the PV efficiency.
15% you can go.
Yes, you can. I want just to give you nominal power is for the PV. For the PV nominal power is 260 watt. Efficiency is 15.78%. What do you need? So we can choose 800. Okay. Yes. No, you are right. It's not with this formula. It's not the power. It is. You can use the same formula with the PV electrical here, but here it is the sun. Yes, you are right. Of course. The surface of the sun.
What is summation of EDI?
Hmm?
EDI in the EX.
Ah, it is the complement, so it is what is lost in terms of exergy. We are speaking about efficiency, or it is called exergy destruction. So, did you find for the electrical, taking the sun temperature? Mm.
Area is also 1 meter square.
Yes, we can take.
Which module you are considering?
It's 200 now. We can reach for this kind of power. Yes. So we can say 1.5. Yes. Okay. I think I've got. I was thinking to put it. Do you? Somebody has. I didn't have the numerical value. If somebody has a value, we can have statistical results. So if somebody give a value, we will see how many people have the same. Do you have it? No?
Efficiency is given. This is power. N is 1. Area is 1.5.
Sorry?
Area is 1.5.
Yes, I took 1.5 square meter. 177?
This will be 1.
It is
0.1 kilowatt. 0.177 kilowatt.
0.1. Okay. Okay, so it's a way to compute this. So after, it's just to show you how it is computed, and after he has also computed for all the data he find. He has managed to make the flow rate changing. Of course, the flow rate of the water circulation is a huge impact, okay, because you cool better the PV function, but you recover less heat because it's more fast, okay. So he find that a good compromise was for flow rate of 2 liter per minute, okay. And he find that it was obviously I didn't take the word. And he find that it was obviously interesting to have phase change in in order to have a gain in the efficiency of the electrical function. Finally, if you win in terms of electrical function, the global exergy efficiency is better, but you can find a compromise between thermal and electrical, and in his case, he find us it was a good compromise with phase change that he chose at 35 degrees in terms of melting, and with a flow rate of 2 liters per minute. Okay, so just an illustration to why in the field of PVT we are using very often exergy to be able to compare, to integrate both thermal and electrical point of view. It's not really my final support. Do you have any question? So very often there is thermal, electrical and economical analysis afterwards to see if it is interesting to use this kind of apparatus for both thermal energy generation and electrical. So we call that thermo, electrical, economical analysis. You will find that in the paper. So if you have no question, we can make a break before the second tutorial. Okay? We make a short break or we continue in the tutorials? Few minutes, maybe? No? Ooh.
5 minutes maybe.
5 minutes, yes. Okay. Hello.
Actually, I'm also working on this PVT,
Yes.
and right now I'm focusing on two ways to extract the heat from the PV panel. Okay, so first
Yes.
one is by using sensible heat extraction, and second is latent heat. So in latent heat, I am trying to use heat pipe.
Yes. Ah, heat pipe,
Heat
it's
pipe,
interesting.
And in sensible heat extraction, so as we know, other than heat pipes, all are coming under the sensible heat extraction only.
Mm.
No phase changing is there, but means in your area, some of the phase changing work is also attached with, means mixed heat extraction process is going on.
Yes.
But earlier only vertical water tubes are there or horizontal tubes are there. In our lab, means my senior is there. Tomorrow he is going to give the lecture also.
Ah, okay.
He's also working on that rectangular spiral type. Means it is a rectangular spiral type structure. And above that,
Me, when for the heat exchanger, we have developed with Patrick Dupéra. You can hear me? Okay. You can keep it if you want. You can keep it. Okay. It's okay? For this last tutorial, previously it was to use a tool, a simulation tool, PolySun, but there is many different kind of tool. What is important in my point of view, if I make the demonstration during 1 hour, the interest is limited. What I want through this tutorial is to show what is behind this kind of tool, okay? And one of the main points is to be able to identify, depending on the localization on the Earth, at each time where is the sun in the sky, exactly. We can, so all these tools have that. You will see it is long equation, but very easy to compute, okay? And so, in principle, if I know my latitude and my longitude, the time zone where I am, I know exactly where is the position of the sun in the sky. There is no uncertainty about that, okay? And it is in this way that the sun tracker are operating. A sun tracker has an electrical engine, okay, and is following the rays of the sun. Okay, it is specially developed for the heliostat, I show you. Of course, the heliostat, the mirror, has to follow the sun and to reflect on the tower. But it is also the case for PV. For PV systems, there is a sun tracker that have one axis, okay? So they are facing, if it's only one axis, generally they are facing the south in the north hemisphere, and they are just following the height of the sun on the sky, okay? But some have two axes, so they at each time following the sun, so they are perpendicular to the direct radiation, okay? How it operates is not the sun tracker has no eye, and no fish eyes, no eye. All is programmed in the sun tracker. That it is most of the case. That explains the reason why, even if it is a cloudy day, if you look at a field of PV with sun tracker, you will see that the sun tracker will move, okay, even if there is cloud, because they know each day at each time where is the sun, and they continue the race, okay? All is programmed through the equation I will show you. So first, it is very important to be able to know that everywhere on Earth, at every time, where is the sun. It is very important for the radiation. So usually such a tool like PolySun are using that, okay? It's not usually, it's for sure. They have all the equation that if you give your localization, the first question is where are you, okay? So you give an address, for example, and they will behind identify the latitude and the longitude, okay? You leave the, so like this, first computation is to convert the local time where you are at what is important. It is what we call the through. I didn't remember. CST. Do you know what is the meaning? It is the through solar time. Okay? Everywhere on the planet there is only one local through solar time. And we know that at this time, at midday at this through solar time, that the position of the sun in the sky is the highest one. Okay? It is zenith. Okay? So whatever the place on the planet, when you are speaking, I want to know at 11 o'clock through solar time where is the sun. It depends of the place where you are, and you know that at this time, at midday through solar time, it is the zenith for you. Okay? But of course, we have to be able to have the same reference. Okay? So the reference will depend on the longitude, and there is one reference in time, which is when you are programming Teams, for example, Teams meeting. Usually you have, so you are programming at your local time, but it gives you a comparison to a reference time, which is Greenwich, GMT. Okay, so you will say GMT plus 8, plus 8, plus 6, minus 5. It is a common Earth reference time. Okay, and so depending on the longitude, you know the longitude, so you will have different between this GMT, Greenwich, so it could be plus or minus. And also there are also other factors. For example, is there a time zone? For example, in India, I discover that for the whole India, it is the same time. So no discrepancy between regard of the longitude. Okay. Whereas in some other country, like Australia, you can have 4 or 5 hours linked to the longitude, okay, of difference, which is a time zone. So this also is depend of the country. So it's not only the longitude, but sometimes it's strange. You have some countries they are not the same hour as they have the same longitude. Okay, but it's a choice, local choice. You have another aspect, which is sometimes some country, it is the case in Europe, they since the petroleum crisis in the 1973, decided that we should change time between winter and summer, and to add 1 hour or to release 1 hour. Okay, so it is also related to local policy. This has been done for energy consumption. I'm not really now fully convinced that there's a real impact between winter and summer to change of 1 hour. I'm not really convinced, but it's still in process. So you see, there's many different times finally, and it is very important to know where we are and which time we consider. In reality, the more important it is the through solar time, locally, okay? But if you made a mistake and use your local time, you can maybe have 2 or 3 hours of difference with the through solar times, and it could be an economical problem if you have made a delay of 2 hours on the estimation of the production. Okay, So it is very important. And so behind all these tools, for sure, there is a programmation of all the times. So as soon as you go in these tools, they ask you, where are you? In which country? Sorry. In which country? And so identify the latitude. So it is PolySun here, for example. He will ask you, where are you? Freiburg in Germany. Then he will compute the latitude, the longitude, and things like this. And it is the same for the tools that I'm using, because we try to develop joint application with this developer, Archelios. The first is to know where is the sun. Second is to know the irradiation. Okay, so this kind of tools also very often are coupling statistical data at the backside that could be found in now there is many data about local irradiation. It could be a mix between satellite. The satellite are providing quite good accuracy in terms of solar potential in every area. Could be a combination with satellite and local meteo that will also statistically identify the number of cloudy day and the number of sunny day, okay, the number of hours. So they are coupled with database. So with this both sides, you are able to exactly, very accurately know what will be the irradiation for 1 month in this area. Usually it's statistically established on 20 years, for example, so it's quite accurate. And the inclination, the direction of the radiation, okay? So if you, then you choose the inclination of your panels, you will know the radiation which is coming. It's also important to deal with that in order to identify the local or the far mask, okay? What could generate shadow. And so, if you don't know the position of the sun in the sky, you will never know the shadow on your panels, okay? Because for sure, if you have a mask, it is between you or your panels and the sun. That means that you have shadow, okay? So it is also important to compute the position of the sun and then to plot what you see also in order to see at what time in the day you will have shadow on your panels. Usually it is, if it is far mask, like mountain, for example, usually it is the morning or the evening, or the morning and the evening, okay? For example, in a plain area where there is no mountain, you will follow the sunrise, okay? Here, I think the sun is starting at 5:30, so if there is no mountain, your panel will start to produce around 5:35, for example, because there is, at the beginning, there is too much reflection, and after stop when there's a sunset, okay? But if you have mountain, it could start, even if the day is here, that don't mean that you have radiation, and it could start around 7. For example, in my place, where there is mountainous in both sides, as I show you to you. In the other side, the mountain is higher. There is a small village at the bottom of the mountain. During winter, is not receiving some direct solar radiation from 10 in the morning, and it stops at 3 p.m. the afternoon. Whereas the day starts at 7 and stop at 7, okay? So it's very important. And also you have the close mask. So it's also very important to know if there is surrounding buildings, to know if there is trees, and so to plot that also between you and the sun, and like this. So what I want to show you is how we simply plot that kind of diagram. I made it with my student, and it is nice to understand this problem of time. It's very important when you are designing to choose a good time, or to be aware of the time compared to the solar through. Okay, so as Pankaj has shown yesterday, there is a declination. The axis of rotation of the Earth and the big rotation of the Earth around the Sun are not in the same plane. Okay, so that means you have a declination, but this declination is changing all over the year. Okay, so minimum is minus 33.45 and maximum 33.45. It is regularly checked. It is very accurate also. In reality, people that are working not with solar energy, obviously, but with air travel or things like this, are using exact value of the declination. Okay. So, for example, you have this. It's in end of December, beginning of January, minus 23. Then in March is 0. For the summer solstice in June, it's a maximum, and then it decreases. Exact computation of this declination. Okay, it is a very long formula, but no difficulty. But it is exact computation. It's not so you can compute it exactly. So in this kind of tools, it is already written. G is the number of the day in the year multiplied by 360 divided by 365. Okay. So for example, the 10th of January, N will be 10. Okay. The 31 of March, it will be 31 day in January, 28 or 29 in February, plus 31. So it will give you the number of the day. Okay. So first, to have an accurate computation of the declination, depending of the day. N is the day, G is the ratio between N of the day. Okay. So here you have the time zone. It is here that you can see that India is the same. Okay. So you can see the choice of some country, even if the longitude. So longitude is like this, and latitude is like this. So longitude will allow to identify the time, okay? Time regarding the sun. And the latitude will allow to determine the best inclination of the panels. The more you are near the equator, the more the latitude is small. And as I show you on Djibouti, or it's the same in Singapore, for example, the panels are almost horizontal. It's around 10 degrees. Okay. The more you are going in latitude with bigger latitude, the more the interest is to become close to the vertical. For example, in Norway or Sweden, when the sun shines, the sun is very low in the sky. Okay, so vertical is a good inclination. It's Double time is good because first the sun rays is low in the sky. The day are small. The sun is low in the sky. And if there is snow, there is a lot of reflection. So if you are vertical, it's good to have a facade that the snow reflects the sun on the facade. So in a way, they are dealing with that. Okay, so you have local time. Okay, local time is related to the UTC. So the time at Greenwich, okay, which is the reference. Depending also of the time zone. So the time zone that is depending of the longitude. Okay. So in terms of solar geometry, what is interesting for us is to know the altitude of the sun in the sky. And so you can have it in degree. That will depend of the declination and the latitude. Okay. So for high latitude, like in Norway, okay. So this becomes small. Okay. So that thing that the rays of the sun in the sky is not high. Whereas when the latitude is small, so near the equator, this stay big, okay? So the rays of the sun is very high in the sky. Okay, so the height of the sun is very important and depend of latitude, but the declination is important too. Equation of time. So due to the fact that the Earth is not doing a perfect circle around the sun, the velocity of the Earth around the sun is not the same. So the more you are close, the more you are fast, okay, by the gravity. Okay, the more you are far, the more you are slow. So the days are not the same because when you are fast and when you are slow, there is small discrepancy, but there is a discrepancy. So that means that at different time in the years, the position, if it was the same velocity, okay, you should have between winter and summer at the same time, okay, time solar through. In winter, the sun is low, then the height is increasing until a maximum during summertime, okay. If it was perfect same velocity, okay, it will be a vertical line. Whereas it's not a vertical line because of the difference of velocity. Okay, there is a small shift at one point for the same time at a different period, different months of the year. Okay, so this is this equation of time that is considering this. So also it's a big formula, but it's not really complicated. So this equation of time give this shift with depending of the day. So you find here the number of the day, and G is the same. It's n multiplied 360 divided by 365. Okay, so you see the difference is minus 6 minutes, so it's not a big difference, but it is depending of the proximity of the Earth relatively to the sun. The velocity of rays is not the same. So the sun is, for us, accelerating a bit in the sky. When we are close, then we are far. Okay, so it's important also because it's almost not the same time. Okay, so when I consider the Greenwich Mean Time or Universal Time, the local time, okay, which is the official time, is UTC or GMT, plus the local zone time, and plus eventually a correction. So you don't have this in India, okay, and you have only one local time finally for the whole country. For some other country, you can have several local time. Okay. What is important is to be able to make the link with the true solar time. The true solar time, a link with the true solar time is the condition to don't make some mistake in the evaluation of the solar potential. So the true solar time will be the reference time, okay, UTC, plus the longitude divided by 15 plus the EOT, so the equation of time. Okay. So all the tools at the backside, when they show you the rays of the sun, be careful, or what is the time? Is it your local time or is it the true solar time? When you find that it is the maximum at midday, it is not at your local time, it is at the true solar time. Okay? By any chance, you can have the same time, but it's rare to have the same time. Okay? So, for example, here, when I am in Chambéry, the 1st of February, okay, I want to know the local time when the sun will be at the maximum. So at the midday through solar time. Okay? You can do the reverse. I can give you the place here, Guwahati, with local time which is 4:45, and ask you what is the true solar time. Okay? So the link with local time and reference time, time zone, and DST, it is if you are a delay between winter and summer, okay, it's +1 or +0. So you don't have it here. Okay? You have your UTC plus time zone, okay? So I don't know how much is it compared to Greenwich here. Plus, okay, so it is plus this and +0, okay? And you have your local time. UTC is the time solar through minus longitude, so divided by 15, minus the equation of time. Okay, and we find that it is 11, a bit more than 11 o'clock. Okay. So in Chambéry, finally, in winter, we are not far from the solar the time solar, the true solar time. Okay. It is midday, whereas midday something, whereas it is midday at sun time. Is it clear all this time and the origin. So it's very important to fully know today at 5:15 here, I exactly know which is the time at the sun. So if I know the time, the sun time, I know the height of the sun in the sky, which is very useful to identify my production. Okay, so for 1st of February, the number of the day is 32. The equation of time related to the formula is around 14 minutes. So I have only a delay of 20 minutes between local time in Chambéry and solar through time. Okay, so thanks to this solar through time, as I told you, as at midday sun, it is the maximum of azimuth. I have a correlation to give me the height of the sun at whatever the through solar time. Okay, so this is how I determine this height of the sun in the sky in my place. Okay. So first important parameter. The other is the place. So the height and the direction. Where is he? So it is the azimuth which is given compared to the south. Okay. So we can compute the altitude angle in terms of angle, and we can also compute the azimuth. Okay, all is depending of the latitude and behind the time solar through. So long equation, but simple to compute. Okay, so yes, this is azimuth. So if I'm in Toulouse, in France, the latitude is 43.6 degrees. In April, I want to know information at 10 hours at solar through time. The day number is 108. The declination is 10.5. The hour angle of the sun is minus 30 degrees. The elevation angles is 47.9, and the azimuth is minus 47.2. So thanks to these two data, I know exactly where is the sun in my place at this time. Okay. Why it is important now is that I can do the same thing with my environment. Okay, I can, if I'm here, so I told that I was looking at the sun, able to know where it is thanks to the angle of 8 and the azimuth. Okay, I can do the same thing if between me and the sun there is a building. I can give the angle, okay, like an azimuth, and I can give an angle in terms of 8 of my building. Okay, so that means that at this time I'm able to plot also a point while considering an obstacle. If I saw here a tree, I'm able to evaluate the angle in terms of 8, okay, and the position facing the south. Okay. So thanks to all these equations that I show you before, each day, each hour of the month of the year in my place, I'm able to compute both the height and the azimuth. and to plot this curve, which finally represent where I'm here, the rays of the sun I see in my place every day of the years. Okay, so this obviously it is for winter, okay, December, and this will be July, okay. So I'm able to plot that. So it's what the tools are doing. They are plotting, for sure, whatever the tools, they will show you this kind of curve. But with my student, I make them done by computation, okay, with an Excel file, finally, and they are able to plot that. You don't have to plot every day a point. You know that it will be this kind of shape. So approximately, you can find 3 points. What is important is 3 points at the worst day, worst month in the year. This curve is important. This curve is important. In between, and here on this kind of diagram, you are able to plot your is at minus 20 degree. So you will be here for minus 20 degree, okay? And the angle 8 will be around 30 because it's okay. So you can plot the tree, okay? So you can plot the tree with 2 parameters, the position with like an azimuth from the south and the angle I see this tree, okay? So it is for close obstacle. But you have also some mountain. Far away, it could be far away, but I see a mountain, okay? For example, far east, I see a big mountain at the east, and so it's the same. It's minus 90 degree, and I estimate the angle of the mountain, and I will plot. Could be something like this. Okay. So like this, I know exactly, and the tools are doing that. At what time of the day you will start to produce electricity, for example. You know that in my area, because there is some mountain, I know that the morning I will never, even during summertime, never produce before 7 o'clock. Be careful, it is, when I have such a diagram, it is solar full time. So it's okay. But if I am in summertime, it's not the same. Okay, could be 8 o'clock locally, and it is 7 o'clock at solar time. So it's very important to know which. If you see such a diagram, for sure it's solar time. Okay. And like this, you know that this tower is from December, January, maybe April, will give you shadow during a certain time in the day. Okay. Of course, this diagram is different depending of the place on Earth. As I told, so Bordeaux is in France, so around 45 degrees of latitude. Oslo, you can see Oslo, Norway. The rays of the sun during winter time is nothing. Okay, very low, almost no sun. And after a bit more, and okay, all the days there is sun during summertime. Okay, and here is Dakar, which is close from equator, so you have a different shape of. So So you have such a thing per localization. So you are able also here to plot that for this place and to see the rays of the sun in your local place, and then to put on this what you see as an obstacle. Okay, it could be close, it could be far, it's the same. If it is between you and the sun, it is shadow, even if it's far. Okay, so you plot the surrounding like this. Here is the tree. What is the position facing the south, and what is the angles in terms of 8, and so I can put it on my diagram. It will be here. Okay, and then I have something else, a house. This could be a mountain. So it's very useful to know that, because finally we don't need tools, but of course the tools are more practical to compute it quickly and to give it, but they are doing this kind of thing. Okay, so first the position, then combining with statistical data about radiation, and then depending of the localization they will identify that. Now it's very well done, because usually they are coupled with Google Street Map. So you have a 3D a description of the environment, and they evaluate by themselves the impact of the local obstacles. When you are giving your address, he know the local obstacle. Of course, it depends on the trees. The trees, it's particular, because if Google has made a scan when there was no tree, or when it was winter time, there was no leaf, you will not see the tree. Tree is difficult. Generally, they don't consider the tree, so you have to be cautious for local tree. They consider, of course, the surrounding buildings, the surrounding house,